not a physical fact. If you've ever been on an airplane cruising steadily at altitude, you have felt a miniature version of this illusion in the quiet of the cabin. When the engines settle into a distant hum and the flight is smooth, you could close your eyes and believe you are sitting in a stationary room. Without a window to reveal the clouds sliding by or the landscape shifting miles below, motion disappears entirely from your awareness. Only when the plane turns, banks, or accelerates does your body register that you are moving at all. This is a subtle trick of physics and biology working together, a conspiracy of the senses that keeps us grounded in a world of constant flight. Our bodies are not built to sense speed itself, but rather acceleration, the sudden changes in velocity or direction that disrupt our equilibrium. Deep within the silent architecture of your skull, your body houses its own ancient navigation system. These are the semicircular canals and the otoliths, tiny, fluid-filled labyrinths that act as the brain's motion detectors. When you start or stop moving, this fluid shifts, brushing against microscopic hairs that send a flurry of electrical signals to your mind, telling you exactly where you are in space. But once motion becomes constant, the fluid stabilizes. It becomes as still as a mountain lake at dawn. The signals stop, and to the brain, no change means no movement. Even though the Earth is constantly rotating, orbiting, and traveling through the void, the absence of sudden lurches means you perceive a perfect, heavy calm. This same sense of stillness tricked early observers for millennia, grounding their philosophy in the evidence of their own eyes. The philosopher Aristotle believed that the Earth was stationary because he reasoned that if it moved, we would feel strong winds constantly blowing in one direction, a gale that would never cease. He thought that if a stone were dropped from a high tower, it would fall behind a moving Earth, landing far from the base instead of straight down at the observer's feet. These ideas matched everyday experience perfectly. No one felt the ground shifting beneath them. Stones dropped exactly where they were intended. The air did not rush away into the dark. It seemed obvious, even undeniable, that the Earth stood still while everything else, the sun, the moon, and the distant stars, moved in a grand, revolving dance around us. It was not until careful measurements, complex mathematics, and the first telescopes entered the human story that this illusion began to unravel. Copernicus proposed that the sun, not the Earth, was at the center of motion, but even he struggled to explain why we couldn't feel the planet's incredible journey. It was later that Galileo showed that motion at a constant speed is indistinguishable from rest. He invited us to imagine being inside a ship moving steadily across calm water. If you were in a cabin below deck, watching water drip from a bottle or fish swimming in a bowl, you could not tell whether the ship was moving or anchored without looking outside. The drops would fall straight down, and the fish would swim with ease in every direction. There is another reason the illusion of stillness feels so complete in our daily lives. The scale of our motion dwarfs human experience in a way that is difficult to comprehend. We evolved to navigate distances measured in steps, meters, and kilometers scales, where a fast horse or a running stream was the limit of speed. The movements of planets and stars happen on scales so vast that even enormous velocities seem invisible. The Earth's rotation might carry you over 1,000 kilometers in a single hour, but compared to the immense size of the planet, that motion is subtle and refined. From your perspective, the landscape beneath you barely changes, and the horizon remains a steady, distant line. We live inside a frame of reference that hides the grand motions from view, tethered to a world that carries its atmosphere and its inhabitants along like a mother holding a sleeping child. When you look at the night sky, the stars appear fixed, but that too is a trick of distance. Each one is moving, orbiting the center of the Milky Way at hundreds of kilometers per second. They only seem still because they are so unimaginably far away. Over the span of a human lifetime, their motion is imperceptible, a frozen snapshot of a much larger journey. Only through long-term observations spanning centuries can astronomers detect their slow drift across the heavens. To the naked eye, the heavens are a painting, a static masterpiece of light. To physics, they are a dance, a swirling, high-speed choreography that never pauses. And yet, this illusion is deeply comforting. It gives us a sense of home, a sense of orientation in a universe that otherwise moves endlessly and without a center. The Earth feels solid, dependable, and safe beneath our feet, precisely because our bodies and senses are tuned to its steadiness. If we could suddenly feel the planet's rotation, the sensation would be overwhelming, a constant rush, a never-ending pull, a dizziness that would make life impossible. Stillness allows life to thrive, not because the world is actually still, but because it moves in a way that makes the perception of stillness possible. The same illusion plays out on smaller scales every day. When you walk through a room, you think you are moving while the room remains stationary. But from another perspective, the room is moving too. It is rotating with the Earth, orbiting the Sun, drifting with the solar system, and moving through the galaxy. You and the room share nearly identical velocities in every one of those motions, and so, relative to each other, you seem still. Motion is always a comparison, a relationship between two things. The illusion of stillness is simply the absence of that difference, a moment where everything in your immediate world is traveling at the exact same pace. This idea can be demonstrated in a thought experiment that strips away our surroundings. Imagine you are floating in the absolute dark of deep space, far from any stars, any planets, or any light at all. There is no window of reference, no way to tell whether you are moving or not. You could be spinning at 1,000,000 kilometers per hour, or drifting gently, or perfectly at rest, and there would be no way to know. Without a reference point to pass by, motion becomes meaningless. In that sense, stillness isn't just an illusion, it is also undefined. This perspective carries an important truth about our place in the cosmos. There is no center of motion, no absolute frame of rest. Everything is relative. The Earth moves relative to the Sun, the Sun moves relative to the galaxy moves relative to the expanding universe. Even the universe itself isn't stationary. Space itself is stretching, carrying galaxies apart like seeds on the wind. Each layer of motion makes the idea of stillness more of a human construct than a universal fact, and yet our experience of it remains deeply real. When you close your eyes and breathe, your heartbeat feels steady and your breath feels rhythmic. You are not aware of the planet turning beneath you, or the sun pulling you around its massive orbit. What you feel is the slow, quiet rhythm of a body that has found equilibrium in motion. Life depends on that equilibrium. Plants follow the sun's arc across the sky without sensing the spin of the world. Oceans rise and fall with tides driven by the moon's pull, a constant movement perceived as a gentle rhythm rather than chaos. The illusion of stillness isn't a failure of perception. It is the brain's way of simplifying a moving world so that we can focus on the small, vital details of living. Sometimes, this illusion breaks for a fleeting moment, and we catch a glimpse of the machinery in motion. When you watch a sunset, the glowing line of the horizon seems to swallow the sun, but what you are actually seeing is the Earth turning away from its star. When you feel dizzy after spinning in place, that is your inner ear protesting the sudden, artificial change in rotation. When you watch a satellite drift across the night sky, you are reminded that objects above us move independently, each following its own path through the void. These moments are small hints that the world isn't as stationary as it feels. It is fascinating that our entire sense of time depends on motion, even though we feel none of it directly. A day is one rotation. A year is one orbit. Our calendars, clocks, and routines are built on cycles of movement that we cannot feel, but only observe. Without that motion, there would be no sunrise or sunset, no seasons, no rhythm to life as we know it. Stillness would mean darkness on one side of the planet forever and endless, scorching light on the other. The illusion of stillness, then, hides a truth. Motion is what allows balance. When scientists measure the Earth's movement, they do it indirectly through its effects. The Foucault pendulum, a device invented in the 19th century, shows the Earth's rotation as a slow change in the plane of the pendulum's swing. Over hours, the pendulum appears to rotate, but it is actually the floor beneath it, the planet itself, that is turning. This simple instrument gives visible proof of the motion hidden in our stillness. The same principle applies to the stars. By tracking their positions night after night, astronomers can detect the slow wobble of Earth's axis and the subtle drift of our planet through space. What feels immovable can always be shown to move, given enough patience and the right tools to see. The illusion extends even deeper into the way we think about our own identity. We often talk about finding balance, about being grounded, as though stability were something fixed and unchanging. But in truth, every sense of balance relies on motion. Your body maintains an upright posture through constant micro-adjustments, tiny, invisible shifts of muscle and bone that keep you from toppling over. Even standing still is an act of continuous movement. The same holds true for the planet and everything on it. Stability isn't the absence of motion, it is motion in harmony. It is remarkable that this harmony emerged at all. The solar system could have formed in chaos, with planets flinging off into space or colliding in violent spirals. Instead, gravity and momentum found an equilibrium that has lasted for eons. The result is a system that moves constantly, yet feels peaceful. Earth's orbit is stable enough to make the perception of stillness possible. You can sleep at night without fear that the world will suddenly veer off course. The sky you see tonight, though filled with moving stars, will look much the same tomorrow. If we were somehow aware of every layer of motion, the spin, the orbit, the drift through the galaxy, our daily lives would be unrecognizable. The simplest act, like setting a cup on a table, would seem miraculous. The cup doesn't slide away despite the planet spinning faster than sound beneath it. That is because motion is shared. The atmosphere, the oceans, the land, the cup, and you all move together relative to one another. Relative to the room, you are still. The illusion of stillness, then, is really the experience of shared motion. This shared motion connects everything from the smallest grain of sand to the largest galaxy. Every object participates in the same fundamental laws. Gravity, inertia, and rotation tie the cosmos together in one continuous network. Your stillness and the motion of a distant star are linked by the same laws of physics. When you realize that, the illusion becomes a comfort rather than a deception. It means you belong to the movement of the universe. Think of a night spent camping far from city lights. The stars wheel overhead, and the air cools as the planet turns. Hours pass, but the ground beneath your sleeping bag feels perfectly still. In reality, you are moving through space in a slow, grand spiral, the entire planet rotating toward the dawn. The stars above you, meanwhile, are gliding through the galaxy, some toward us and some away. Every point of light is part of an immense circulation. Yet, the scene feels peaceful because all those motions combine into a profound stability. This balance is delicate, and even small changes can break the spell. The Earth wobbles slightly on its axis, a motion called nutation, caused by the gravitational influences of the Moon and the Sunday. Over long time scales, these wobbles shift the climate, bringing ice ages that come and go, reshaping oceans and continents. Even when the illusion seems perfect, motion is quietly altering the world. Stillness never truly lasts, but it also never vanishes. It is reborn continuously as movement settles into new harmony. This may be the most profound truth hidden in the illusion. Stillness isn't the opposite of motion, but the feeling we have when motion is perfectly balanced. The Earth spins just right to keep the day steady. It orbits the Sun at the perfect distance to keep the climate stable. The Sun moves through the galaxy in a way that preserves the structure of the solar system. Everything flows, but because it flows together, we experience calm. So when you sit quietly and the world feels unmoving, you are feeling the equilibrium of cosmic motion. You are, in that moment, perfectly synchronized with the spinning, orbiting, drifting machinery of the universe. You are part of its smoothness, its rhythm, and its illusion of rest. If you were to stand outside on a clear night and look toward the horizon, the world around you would seem perfectly still. The trees would sway in the wind, the stars would remain steady in their places, and nothing about the ground beneath you would suggest that you are moving at all. Yet, that calm, solid surface is turning constantly. The Earth spins beneath everything we know, and it has done so since before there was an ocean, before there were continents, and before there were eyes to watch the sky. Every day, every night, every second, the planet rotates smoothly, silently, and endlessly. It is difficult to picture what that means, because stillness is the only motion we ever truly feel. But imagine this. At the equator, the ground is moving eastward at about 1,670 kilometers per hour. That is nearly half a kilometer every single second. If you stood there and the rotation suddenly stopped, you would be flung eastward faster than the speed of sound. The oceans would roar from their basins. The atmosphere would tear away in shock waves, and mountains would crumble under the sudden shift. Thankfully, it never happens. The Earth turns with a grace that is almost impossible to comprehend, a speed so constant and uniform that the world feels peaceful, even as it moves at an extraordinary velocity. That rotation defines almost everything we experience about the passage of time. Day and night are not things that happen to Earth. They are things Earth creates through its spin. When the planet turns toward the sun, we call it morning. When it turns away, we call it night. The slow, predictable turning of the planet brings light, shadow, warmth, and rest in a steady cycle that has shaped every rhythm of life. Plants open their leaves when sunlight arrives and close them when it fades. Animals move and sleep by the turning sky. Humans learned to mark this motion long before they understood what caused it, measuring days by the rising of the sun and the length of shadows cast on the ground. From the perspective of a satellite in high orbit, the planet's surface would slide beneath you like an endless tapestry of oceans, deserts, forests, and clouds. The atmosphere would swirl and shimmer, forming hurricanes that twist in opposite directions depending on which hemisphere they occupy, turning clockwise in the south and counterclockwise in the north. This swirling motion is a result of the Coriolis effect, a phantom force born from the rotation itself. It is the hidden hand that organizes the weather and climate systems of our world, guiding the flight paths of airplanes and the deep, slow currents of the oceans. But the spin does more than just move the air. It reshapes the very planet beneath your feet. Because we are turning, a centrifugal force pushes outward at the equator, fighting against the pull of gravity. It is enough to make you weigh a tiny bit less at the center of the world than you would at the frozen, silent poles. The difference is small, less than 1%, but it is measurable and real. This force makes the planet bulge at its middle and flatten at its ends, giving our home the shape of an oblate spheroid rather than a perfect sphere. A difference of 21 kilometers in radius exists between the equator and the poles, just enough that satellites must account for it as they drift through the void, and just enough to remind us that the Earth is not a static sculpture, but a fluid, moving body. If you were to trace the Earth's axis, the invisible needle around which we spin, you would find it pointing toward a quiet spot in the northern sky near the star Polaris. For centuries, this star has been our North Star, a fixed beacon for travelers and navigators who looked up and found their way home. But the axis is not perfectly still. It stays tilted at an angle of 23.5 degrees as we journey around the sun, giving us the shift of seasons, the long golden days of June, and the deep biting nights of December. Over tens of thousands of years, however, this axis slowly wobbles, tracing a wide, patient circle in the sky in a motion called precession. We do not notice it in our short lifetimes, but in 13,000 years, the bright star Vega, not Polaris, will be the North Star, and the heavens will have shifted their center once again. We live in a world governed by clocks, but the Earth is the grandest clock of all. Scientists today measure its rotation with a precision that borders on the miraculous. Using atomic clocks and radio signals bounced off distant, ancient quasars at the very edge of the observable universe, they can track tiny variations in the planet's spin down to fractions of a millisecond. These fluctuations happen because the Earth is alive with a constant exchange of energy. Strong winds, melting ice, and even massive earthquakes can subtly alter how fast we turn. When great glaciers melt and their mass is redistributed toward the oceans, the planet's spin adjusts, much like a figure skater, extending their arms to slow down or pulling them in to speed up. After the massive earthquake in Japan in 2011, the redistribution of the Earth's mass was so significant that the day actually shortened by about 1.8 microseconds. These changes are minute, imperceptible to our human senses, yet they reveal how interconnected everything is, how the deep structure of the planet and the flow of its molten core influence the turning of the world above. This steady rhythm is the foundation of our biology. Our bodies carry internal clocks called circadian rhythms, which have evolved over millions of years to synchronize with the 24-hour day. This rotation provides the signal that tells plants when to photosynthesize, animals when to hunt or rest, and people when to drift into sleep. Without it, the balance of every ecosystem would collapse. But the spin provides more than just a schedule. It provides a shield. Deep beneath the crust, the rotation stirs the molten iron of the outer core, creating a dynamo effect that generates a massive magnetic field. This invisible shield deflects the lethal charged particles of the solar wind and cosmic rays from deep space, protecting our atmosphere and life itself. Without the rotation, this dynamo would weaken, and the solar wind would strip away our air, leaving us a barren, silent husk. Our spinning world does not just give us day and night, it gives us safety. Sometimes, the illusion of stillness breaks just slightly, and we can sense the spin indirectly. You might visit a museum and find a Foucault pendulum, a heavy brass ball swinging freely from a long, thin wire. As you watch it over the course of an hour, you will see that it slowly changes its direction relative to the floor beneath it. But the pendulum is not turning, the Earth is. Watching it is like watching the invisible motion of the world made visible. The fact that the Earth spins so smoothly also affects the very flow of time. Our definitions of seconds, minutes, and hours are derived from this motion. Occasionally, when the planet's rotation drifts slightly due to natural fluctuations, we must add or remove what is called a leap second to keep our atomic clocks aligned with astronomical time. It is a small human correction to a cosmic rhythm, a reminder that even the steadiest spin is alive with subtle variation. Astronauts see this more clearly than anyone. On the International Space Station, circling the Earth every 90 minutes, they watch 16 sunrises and 16 sunsets in a single 24-hour period. To them, the planet spins beneath in a blur of blue and white, continents sliding silently past their windows. They describe the view not as dizzying, but as graceful, a motion so vast and smooth that it feels as if the planet itself is a living being. From their vantage point, the thin blue line of the atmosphere is the only thing separating the vibrant life below from the cold, indifferent vacuum of space. Every sunrise they witness is proof of motion, and every shadow that shifts across the continents is a quiet demonstration that the Earth is in constant, tireless rotation. As you sit here listening, the ground feels fixed, but you are moving faster than any storm. The stars seem still, but their apparent motion from dusk to dawn is a direct result of the Earth's spin. We often describe time passing as the sun rising and setting, but it is really the Earth turning and turning again. The rhythm of our days is the rhythm of rotation. And yet, this motion is only the beginning of our journey. Even as we spin, we are engaged in a much grander voyage. The Earth does not only turn on its axis, it travels around the sun, following a wide, looping path that defines the length of a year. This is the Great Orbit, a journey so vast that no one can ever feel it. Yet every season we experience is a milestone along its path. If you could step back far enough from the Earth, away from the planets, and look down from above the sun's north pole, you would see the whole solar system arranged like a grand, glowing wheel. The planets would appear as tiny beads of light, tracing their orbits around the center, each moving at its own pace. Mercury zips around in just 88 days, while Venus takes 225. Earth glides along its path once every 365.25 days, while Mars, slower still, takes nearly 2 Earth years to complete its turn. The farther a planet is from the Sun, the longer and slower its orbit becomes, each one obeying the same laws of motion that keep the entire system in a delicate, beautiful balance. The shape of Earth's path is an ellipse, a gentle oval, not a perfect circle. The Sun sits slightly off-center within this oval, which means that over the course of a year, our distance from the star changes. In early January, we reach a point called perihelion, where we are closest to the Sun, about 147 million kilometers away. In early July, we reach aphelion, our farthest point, at 152 million kilometers. Many people imagine that summer happens when we are closest to the Sun, but the difference in distance is too small to cause the seasons. Instead, it is the tilt of the Earth's axis that brings warmth and light to one hemisphere, while the other leans away into the cold. The distance change only makes a small difference in the intensity of sunlight, but it is enough that our planet's orbit breathes slightly a slow, rhythmic in and out motion as we circle our star. The speed of this orbital motion is extraordinary. The Earth travels at roughly 107,000 kilometers per hour along its path. In a single second, it moves about 30 kilometers through space. Every minute, you travel nearly 2,000 kilometers. By the time you finish this thought, you will be thousands of kilometers farther along the planet's path around the Sun than you were just a moment ago. Though you feel nothing, the orbit is smooth and steady, a perfect balance between two forces that never stop acting on each other: gravity and momentum. Gravity, the pull of the Sun's immense mass, tries to draw the Earth inward, while the momentum of our planet tries to send it flying outward into the dark. The result is neither falling in nor escaping, but a continuous freefall that loops forever. The Earth is always falling toward the Sun, but never reaching it because its sideways motion keeps it perpetually missing its target. This balance was first described by Johannes Kepler in the early 1600s. He discovered that planets move in ellipses and that their speeds change slightly as they move closer to or farther from the Sunday. When the Earth is near perihelion, it moves faster. When it is near aphelion, it slows down. The total energy stays the same, but the exchange between kinetic and potential energy creates a graceful variation, like the steady breathing of a cosmic lung. Later, Isaac Newton showed why this happens. explaining that every mass attracts every other mass. The same force that keeps an apple on the ground keeps the Earth in its orbit. It is a humbling thought that the vast architecture of the solar system is governed by the same rules that shape the fall of a pebble or the swing of a pendulum. The Earth's orbit may be grand, but it is part of a universal order that extends from the smallest grain of dust to the largest galaxy. The orbit also defines the rhythm of the seasons through the tilt of our axis. As we move around the sun, each hemisphere alternately leans toward or away from the light. When the northern hemisphere tilts toward the sun, it experiences summer, longer days, higher sun angles, and more direct light. At the same time, the southern hemisphere tilts away and experiences winter. Spring and autumn come when the tilt neither favors nor opposes the sun, and day and night are nearly equal across the world. This simple tilt, combined with our orbital motion, gives rise to almost everything we associate with time and change. The migration of animals, the growth of plants, and the weather patterns that shape our lives. It is easy to take for granted that our orbit is stable, but in the long history of the solar system, stability was earned through chaos. When the planets first formed, their paths were violent and unpredictable. But over millions of years, the orbit settled into the patterns we see now. The fact that our orbit is nearly circular is one of the quiet reasons life could flourish here. A more elongated orbit would bring dramatic, lethal changes in temperature. The Earth leaves no wake as it moves through the vacuum of space, yet its path is illuminated by the sun and tracked with astonishing precision by modern science. We can measure our position to within centimeters, using laser-ranging experiments that bounce signals off reflectors left on the moon. The timing of radio pulses from distant pulsars, the behavior of spacecraft, and the alignment of celestial events all confirm the extraordinary accuracy of our knowledge. The orbit may be invisible, but it is not uncertain. Every second, scientists can tell you almost exactly where the Earth is in its endless path. This mathematical precision is what allows us to predict eclipses, transits, and celestial alignments far into the future with breathtaking accuracy. It is the same quiet certainty that allows us to send spacecraft to other planets, timing their launches so they intercept their targets along their own complex orbits. Every interplanetary mission is a direct application of the same principles that keep the Earth moving. The delicate, eternal balance between gravity and momentum. The laws of motion that describe our orbit also describe the flight of every probe and rover exploring the solar system. Despite all that motion, the sense of stillness remains. You can go outside on a quiet morning, feel the ground firm beneath your feet and the sun's warmth on your face, and nothing about that experience suggests that you are hurtling through space at tens of kilometers per second. The orbit is too large, too smooth, to leave any trace of motion in your senses. What you feel is equilibrium, the same delicate balance that defines all motion in the universe. If the Earth's orbital speed were even slightly slower, we would fall closer to the sun. If it were faster, we would drift farther away into the freezing dark. The exact speed we have is what keeps us in a stable, life-supporting zone. This region, often called the habitable zone or the Goldilocks zone, is where temperatures allow liquid water to exist on a planet's surface. It is a narrow range, neither too hot nor quite cold, and the Earth's orbit sits comfortably within it. Small changes could make enormous differences. A shift of even a few percent in our distance from the sun would alter the climate dramatically. Yet, for billions of years, the orbit has held steady enough to allow life to evolve and persist. The tilt of the axis and the orbit together give rise to a complex dance of light that unfolds over the course of each year. The sun's position in the sky changes not only in height, but also in the length of its path from sunrise to sunset. Near the equator, the change is small. Near the poles, it is immense. In the far north and south, there are times when the sun never sets, and others when it never rises. These extremes are expressions of geometry, the tilt and orbit working together to paint the shifting boundaries of day and night across the planet's surface. When you consider the scale of this motion, it is easy to forget that the Earth's orbit is only a small part of a much larger story. The Sun itself is moving around the center of the Milky Way at about 230 kilometers per second, taking the planets with it. That means our orbit is carried forward in a giant spiral, each loop a new step along the galaxy's arm. The Earth never travels the same path twice. Each year's circle is drawn in a different place in space, a beautiful winding helix through the stars. The journey is continuous, unending, and quietly magnificent. If you could watch this from outside the galaxy, you would see the solar system as a cluster of tiny lights following a glowing trail, the sun leading, the planets swirling behind like sparks in a gentle current. The Earth's orbit would look like a fine thread in that pattern, barely visible against the immensity of the Milky Way. And yet, from our point of view, it is everything. That single loop is where all of human history has unfolded. Every thought, every life, every dream has happened somewhere along that unbroken path. The awareness of this motion changes nothing about how the world feels, yet it deepens the sense of belonging to something vast. The orbit does not ask us to do anything. It simply carries us. It defines the rhythm of time, but it never interrupts. The seasons turn, the sun rises and sets. The Earth continues along its endless trajectory, never hurried, never delayed. And as it does, it brings along all the companions of the solar system, planets, moons, asteroids, and comets, each one moving to its own beat within the shared gravitational web. Together, they create a choreography of motion around the sun, a quiet dance that has been unfolding for billions of years and will continue long after this particular year. This particular moment has passed into memory. The sun, the great center of our solar system, feels like the most stable point we know. Every morning, it rises in the same direction, glowing with the same light, anchoring our sense of time and place. For most of human history, it was thought to be unmoving, a fixed point around which everything else revolved. But the truth is quieter, deeper, and far more fascinating. The sun, like everything else in the universe, is in motion. It has been moving since before the Earth existed, tracing its own vast orbit through the Milky Way. The light that warms your skin and the gentle gravity that holds the planets in their places all belong to a star that is itself a traveler, crossing into stellar space on a journey that will last hundreds of millions of years. The Earth does not orbit a stationary object. It follows a star that is always on the move. The Sun is one of roughly 200 billion stars in our galaxy, each one following its own path around the galactic center. If you could somehow step back and watch from far above the Milky Way, you would see a vast rotating disk of light, a spiral of stars, gas, and dust, all turning slowly around a dense, invisible hub. Near the center lies a supermassive black hole about 4 million times the mass of our Sun, hidden by clouds of gas and dust, but exerting a gravitational influence over the entire galaxy. Every star, including the Sun, orbits that center, caught in its deep gravitational well. The Milky Way is enormous. From one side to the other, it spans about 100,000 light-years. The Sun sits roughly halfway out from the center, about 27,000 light-years away, nestled in a region between two spiral arms called the Orion Spur. Here, the Sun and its planets orbit the galactic center at a speed of about 230 kilometers per second, fast enough to circle the galaxy once every 230 million years. That means that since the Earth formed about 4.5 billion years ago, the solar system has made nearly 20 complete orbits around the Milky Way. Every era of life, every extinction, every rise of civilization has happened during one tiny segment of that immense journey. The path the sun follows isn't a simple circle. It moves in a slightly wavy orbit, bobbing up and down through the plane of the galaxy as it travels around. Sometimes it is a little above the galactic disk, sometimes below, moving in a kind of gentle oscillation. It also drifts slightly inward and outward, tracing a slow spiral that changes subtly with each revolution. These motions are caused by the gravitational pull of other stars, giant molecular clouds, and the uneven distribution of mass throughout the galaxy. The result is that the sun's path is more like a long, slow ripple through a sea of stars than a perfectly flat orbit. If you could see this motion from outside, it would look serene. The sun would glide smoothly along, dragging its retinue of planets behind it, each one looping around in a spiral pattern. Mercury closest, then Venus, Earth, Mars, and the rest, all tracing graceful helices through the interstellar dark. To the human eye, it would look almost like a glowing thread unwinding in space. Each loop of the Earth's orbit would be a small twist along that thread, never overlapping exactly, each one farther along the galactic path than the last. It is a continuous voyage, not a closed circuit. The solar system never returns to the same place twice. The region of the galaxy we pass through is not empty. It is filled with thin clouds of gas and dust, remnants of long-dead stars and raw material for new ones. The sun and its planets currently travel through a region known as the local interstellar cloud, a sparse, wispy patch of hydrogen and helium gas stretching about 30 light-years across. It is part of a larger structure called the local bubble, a cavity in the galactic disk created millions of years ago by a series of supernova explosions. Those ancient blasts swept away the surrounding gas, leaving behind a low-density region that the sun happens to be passing through. Even though the interstellar medium is extremely tenuous, with fewer than 1 atom per cubic centimeter, it still interacts with the solar system in subtle ways. The solar wind, a constant stream of charged particles flowing outward from the sun, meets the thin gas of interstellar space at a boundary called the heliopause. This is the edge of the sun's influence, the outer boundary of the bubble carved by its wind. Beyond that point, the particles from the sun slow down and merge with the surrounding interstellar medium. Spacecraft like Voyager 1 and Voyager 2 have crossed this boundary, becoming the first human-made objects to enter interstellar space. They still move with the sun, but they now drift in the same vast ocean through which our star sails. As the sun travels, it carries the entire solar system along with it. Planets, moons, comets, and asteroids are all bound together by its gravity. Every particle that orbits the sun shares this motion. The comets in the distant Oort cloud, stretching perhaps halfway to the nearest stars, form the outermost fringe of the solar system's domain, and even they move with the sun through the galaxy. The scale is staggering. The solar system's influence extends for trillions of kilometers, yet it remains just a tiny speck compared to the distances between stars. The nearest neighboring star, Proxima Centauri, lies about 4.24 light-years away, roughly 40 trillion kilometers. In its orbit, the sun moves among other stars that are also on their own paths. Some drift alongside us for a time before slowly diverging. Others pass nearby, changing the distribution of comets in the Oort cloud, or slightly altering the sun's motion through their gravity. Every few million years, a star comes relatively close to our solar system, close in cosmic terms, though still many trillions of kilometers away. These encounters are gentle but cumulative. They subtly reshape the long-term trajectory of the sun and the architecture of the solar system, reminding us that even on this grand scale, nothing moves entirely alone. The motion of the sun through the galaxy is not random. It follows the collective flow of the Milky Way's disk. where most stars move in roughly the same direction around the center. The entire disk itself rotates, though the rotation is not uniform. Stars closer to the center move faster than those farther out, a pattern known as differential rotation. This means that over time, the spiral arms of the galaxy do not stay fixed. They shift and reform like waves on a slow-moving sea. The sun's journey carries it through these spiral arms periodically, passing through regions of higher density where stars are born, and then moving into calmer, emptier regions between them. Astronomers think the sun completes one circuit around the galaxy roughly every 230 million years. But the precise duration of a galactic year can vary slightly depending on the method of measurement. To put that in perspective, one galactic year ago, during the sun's previous full orbit, the earliest dinosaurs were walking on Earth, and the first mammals were just emerging. Every revolution of the sun around the Milky Way marks a new chapter in the planet's deep history, written not in human years, but in cosmic age. Our star has crossed spiral arms, passed through interstellar clouds, and shared space with countless new stars. Its journey is one of motion through both space and time, not just across distance, but through epochs. Each orbit around the Milky Way is a new sweep of history, carrying whatever worlds and life it sustains into the next chapter of cosmic evolution. When you look up at the sun from Earth, it is easy to think of it as the fixed, unmoving center of everything. But in truth, it is as much a traveler as any of us. It is a moving beacon of light, leading its small family of planets through the vast, cold darkness of the galaxy. Every sunrise is a moment on that voyage, another turn along the galaxy's endless curve. The light that spills across the world each morning comes from a star that is never in the same place twice. And as it continues onward, it carries us with it, Earth, Moon, and all through the wider, silent sea of stars. The path it follows is one thread among billions. Each star weaves its own trajectory, altogether forming the living, breathing structure of the Milky Way. The sun's motion is just one piece of that grand, quiet movement, the background current that pulls everything along. The solar system, bound tightly to its star, drifts through the galaxy not as a single dot, but as a miniature world in motion. Planets orbiting, moons circling, comets sweeping past, all drawn forward by the same unseen hand. The sun does not travel through the galaxy alone. Around it, bound by gravity and moving in perfect rhythm, the planets, moons, asteroids, and comets trace their own intricate patterns through space. Each one follows a path that seems simple from a distance, but becomes endlessly complex the closer you look. Together, they form a structure, both stable and dynamic, a family of worlds orbiting a common star, each influenced by the others, all sharing the same great motion as they journey around the Milky Way. The solar system is often imagined as a flat diagram, a series of concentric rings drawn around a glowing center, but in truth, it is far more alive. Each planet moves at a different speed, along a slightly tilted plane, creating a three-dimensional choreography that never stops. From the smallest asteroid to the largest gas giant, everything that circles the sun is part of the same gravitational conversation. Some move quickly, looping around the star in months. Others drift slowly, taking centuries to complete a single orbit. But together, they create a pattern that has remained balanced for billions of years. At the heart of this dance lies gravity. It is the silent conductor of motion, the force that binds everything to everything else. The sun contains about 99.8% of the solar system's total mass, and its gravity shapes the orbits of all the planets. Each planet, in turn, exerts a smaller pull on the sun and on its neighbors. The result is a complex web of interactions that can be described with mathematics, but is easier to imagine, as a graceful perpetual motion, a collection of bodies moving in harmony, their mutual pulls creating a system that remains coherent despite its constant, restless movement. The innermost world, Mercury, moves the fastest. It whirls around the Sun every 88 days. Its small orbit, almost circular but slightly stretched, as if it were straining against the Sun's overwhelming grip. Its surface, cratered and scorched, faces temperatures that swing from freezing to blistering in the span of a single rotation. Because it is so close to the Sun, Mercury experiences strange effects from gravity. Its orbit slowly rotates over time, a phenomenon known as precession. This subtle motion was one of the first clues that Newton's laws, though remarkably accurate, were not the whole story. Only Einstein's general theory of relativity could fully explain the precise rate of Mercury's orbital shift, showing that even in this small inner part of the solar system, space and time are slightly curved by the Sun's immense mass. Farther out lies Venus, almost the twin of Earth in size, but utterly different in nature. Its thick, suffocating atmosphere traps heat so efficiently that its surface stays hot enough to melt lead. Venus moves around the Sun once every 225 days, but its rotation is peculiar. It spins backward compared to most other planets, meaning that on Venus, the Sun rises in the west and sets in the east. It also rotates very slowly, taking 243 Earth days to complete a single turn, a period longer than its own year. The result is a world where day and night, heat and shadow, unfold at a pace so alien that no human rhythm could follow it. Yet, Venus remains locked in step with the solar system's overall pattern, circling steadily in its place, contributing to the gravitational balance that defines the whole. Then comes Earth, our moving home, orbiting at an average distance of about 150 million kilometers from the Sun. It travels at just the right speed, not too fast, not too slow, to maintain a nearly circular path. That balance, achieved through billions of years of evolution, keeps the climate within the range that allows liquid water, weather, and life. The Earth's motion is not isolated. It is constantly influenced by the Moon, by Venus, and even by the distant pull of Jupiter. Tiny changes in its orbit accumulate over long timescales, causing slow variations known as Milankovitch cycles that have shaped ice ages and climate shifts throughout history. Even something as stable as a planet's orbit carries traces of interaction with the rest of the cosmic dance. Beyond Earth lies Mars, smaller, colder, and marked by a landscape of deserts, mountains, and deep canyons. Mars orbits the Sun once every 687 Earth days, nearly twice the length of our year. Its thin atmosphere and tilted axis give it seasons much like Earth's, though they are more extreme and longer lasting. Mars and Earth occasionally align on the same side of the Sun, coming close enough that spacecraft can travel between them with relative ease. The gravitational interplay between the two, though faint, subtly affects their orbits, showing that even across millions of kilometers, the planets are never truly separate. Past Mars lies the asteroid belt, a vast region filled with rocky fragments, remnants of a world that never formed. These asteroids range from tiny pebbles to dwarf planets hundreds of kilometers across. Their orbits form a kind of transitional zone between the inner rocky planets and the outer gas giants. The belt itself is shaped by Jupiter's gravity, which prevents the material from coalescing into a single planet. Instead, the asteroids remain in a delicate balance, their paths shaped by resonances with Jupiter's motion. Some are drawn into stable patterns, while others are flung away into the dark. The belt is not as dense as old depictions suggested. It is mostly empty space with vast distances between each object. But in the grand choreography of the solar system, it serves as a kind of rhythm, a quiet pause before the slower, deeper motions of the outer worlds. Dominating the outer system comes Jupiter, the giant among planets. It contains more mass than all the other planets combined, and its gravity influences not only its own moons, but the entire architecture of the solar system. Jupiter orbits the Sun once every 12 Earth years, moving at a speed slower than Earth's, but with far greater momentum. Its presence stabilizes some orbits and disrupts others. Without Jupiter, the inner planets might have faced far more frequent impacts from comets and asteroids. Many of those objects are either captured by Jupiter or flung outward into distant space. The balance of safety and danger that defines Earth's long-term habitability owes much to this giant, steady presence. Saturn follows a world of rings and shadows. It is slightly smaller and less dense than Jupiter, but still immense. Saturn orbits the Sun once every 29 years, its path marked by the glow of its icy rings. These rings are made of particles of ice and rock, each one following its own miniature orbit around the planet. They are a kind of echo of the solar system itself, a smaller-scale version of the same pattern where countless bodies, each moving according to gravity, form a single coherent structure. Saturn's moons, too, participate in this harmony. Some orbit within gaps in the rings, while others tug gently on them, shaping their edges and divisions. The entire system of Saturn is a microcosm of the solar system's larger dance, a perfect demonstration of motion and order coexisting in complexity. Beyond Saturn lies Uranus, the first planet discovered in modern times with the aid of a telescope. Its orbit takes 84 Earth years to complete, and its rotation is tipped dramatically. It spins almost on its side, as if it were rolling along its path. This extreme tilt gives Uranus seasons that last more than 20 Earth years each. For decades at a time, one pole faces the Sun continuously, while the other lies in deep darkness. The cause of this tilt may have been a colossal impact early in its history, yet even with this unusual orientation, Uranus moves in harmony with the rest, following the same gravitational rules that bind the entire system. Farther still, Neptune completes the visible family of planets. It orbits once every 165 Earth years, tracing the outer edge of the planetary system. Beyond it, in the dim reaches where sunlight grows weak, lies a region filled with icy worlds, the Kuiper Belt. Here are objects like Pluto, Eris, Haumea, and Makemake, small and cold, each following its own path along the frozen frontier. These dwarf planets remind us that the solar system does not end at Neptune, but continues outward in a slow fade, where the boundary between the Sun's influence and interstellar space gradually blurs. Even beyond the Kuiper Belt lies the Oort cloud, a vast sphere of icy bodies extending perhaps halfway to the nearest stars. These distant comets orbit the Sun on paths so long that a single revolution might take millions of years. Some are disturbed by passing stars or the tidal forces of the Milky Way, sending them inward toward the planets, where they become bright comets visible from Earth. Every comet that crosses our sky is a messenger from that outer realm, a trace of the solar system's distant edge, entering briefly into our neighborhood before retreating again into the dark. All of these objects, planets, moons, asteroids, and comets move together, bound by gravity and time. Their orbits are stable enough to last for billions of years, yet flexible enough to respond to subtle changes. The solar system's stability is not static, but dynamic. The planets constantly adjust to each other's presence, exchanging tiny amounts of energy through gravitational tugs. This process is called orbital resonance, and it appears throughout the system. Jupiter's moons, for example Io, Europa, and Ganymede, are locked in a precise resonance, where for every orbit Ganymede completes, Europa orbits twice, and Io orbits 4 times. This regular pattern keeps their orbits stable and creates tidal forces that generate internal heat. On Io, that heat drives constant volcanic activity, making it the most volcanically active world in the solar system. On Europa, it likely maintains a subsurface ocean beneath the ice, a potential habitat for life. The Sun, massive though it is, does not remain perfectly still at the center of the system. The combined gravitational pull of the planets, especially Jupiter and Saturn, causes it to move slightly in response. The Sun and planets all orbit a common center of mass called the barycenter, which sometimes lies just outside the Sun's surface. This means the Sun wobbles gently as the planets move, shifting position in a slow, subtle way. Even the star itself participates in the dance, responding to the gravity of its companions. The entire solar system is thus a single, interconnected structure, each part influencing every other, every motion contributing to the whole. This dance also connects to the origins of everything we see. The same rotation that keeps planets in orbit once shaped their formation. When the Sun was young, it was surrounded by a disk of gas and dust rotating around it. Over time, that material clumped into larger and larger bodies, colliding, merging, and settling into the orbital plane. What we see now is the long-term outcome of that original disk motion that began billions of years ago and never stopped. The solar system is not a static arrangement of objects, but an ongoing process. Each orbit is a continuation of motion inherited from the birth of the Sun itself. The gravitational links between them extend across space, creating invisible lines of force that connect every world to every other. From our small vantage point on Earth, this might seem abstract, but it is the foundation of everything we know: the predictability of sunrise, the stability of seasons, the long-term safety of our orbit. Beyond the Sun's gravity, beyond the farthest edge of the Oort cloud, lies the galaxy that holds it all, the Milky Way. To the gazer from Earth on a clear night, it appears as a pale band of light stretched across the sky, faint and misty, like a distant cloud. But that soft glow is not a cloud at all. It is the combined light of hundreds of billions of stars woven together into a single enormous structure, one that is itself in constant motion. The Milky Way may look serene and unchanging from our porch, but it is a rotating system of unimaginable power, a vast spiral of stars and shadows turning slowly around a heart that we are only just beginning to understand. If you could see the Milky Way from far above, from some imaginary vantage point outside its disk, you would see a spiral with long, graceful arms curling outward from a bright core. These arms are not solid structures, like the blades of a fan, but patterns regions where gas and stars are more densely packed, moving in waves that travel through the galactic disk. The stars themselves move in and out of these arms like cars in slow-moving traffic, gathering briefly in the congestion and then drifting apart again as they find the open road. These spiral arms are places of birth, where clouds of gas collapse under the weight of gravity to form new stars. Over time, the young stars drift away, and new ones take their place, yet the pattern persists. It is not a fixed sculpture of light, but a living, shifting design that constantly renews itself. The galaxy's structure is immensely complex. At its center lies a bulge, a dense, spherical region filled with old stars and ancient orbiting clusters. Inside that bulge, hidden by thick curtains of dust and gas, is the galactic center, where a supermassive black hole called Sagittarius A times resides. This black hole, about 4 million times the mass of our Sun, anchors the inner region of the galaxy. It does not act like a vacuum devouring everything nearby, as popular myths might suggest, but it exerts an enormous gravitational pull that helps shape the orbits of the stars around it. In the region close to it, stars move at incredible speeds, completing full orbits in mere decades. The closer you get to the center, the faster the motion becomes a swirl of gravity, that defines the very heart of the Milky Way. From that core, the galaxy extends outward through its spiral arms, the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and others, stretching tens of thousands of light-years into the dark. Our Sun is located between two of these in a smaller structure called the Orion Spur, a quiet, relatively stable region about halfway from the center to the outer edge. Here, the density of stars is moderate, and the environment is calm compared to the crowded, chaotic inner regions. Yet even this calm is full of motion. Every star, including our Sun, is moving at hundreds of kilometers per second, orbiting the galactic center in a vast, slow rotation that takes roughly 230 million years to complete. To imagine what that means, consider this. Since the Sun's formation, about 4.6 billion years ago, it has circled the Milky Way roughly 20 times. Each orbit marks an era, not of human history, but of planetary and biological history. The last time the Sun was in this exact part of the galaxy, the first dinosaurs were just beginning to walk the Earth. The rise and fall of continents, the evolution of complex life, the formation of mountains and oceans, all of it has unfolded across the long march from simple cells to conscious beings, all within the span of a few galactic rotations. Each full turn of this ancient wheel encompasses millions of generations of life, and yet to the galaxy itself, it is just one cycle in a multi-billion-year journey. The Milky Way's rotation is not uniform. Like all spiral galaxies, it exhibits what astronomers call differential rotation. The inner regions revolve faster than the outer ones. Stars closer to the center complete their orbits in shorter times, while those near the edge take much longer. This means that over time, the spiral arms would seem to wind tighter and tighter if they were made of fixed material. But because they are density waves, moving patterns, rather than solid structures, the galaxy's form remains open and stable. The arms are like ripples on water traveling through the medium of stars and gas, creating the appearance of a cohesive shape, while the individual components are in constant flux. Surrounding the flat disk of the galaxy is a halo, a vast, roughly spherical region that extends far beyond the visible edge of the stars. The halo contains ancient stars, globular clusters, and an even more mysterious component, dark matter. Though invisible, dark matter makes up most of the Milky Way's mass. It exerts gravity, shaping the orbits of stars and gas, but it does not emit or absorb light. Without it, the galaxy's stars would be moving too fast to stay bound together. They would fly off into the intergalactic void. The fact that they remain together is one of the strongest signs that dark matter is real. The Milky Way's motion, therefore, is not just a matter of the visible stars and gas, but of the unseen substance that holds them all in place, an invisible scaffolding for the light we see. Within this structure, everything moves relative to everything else. The stars orbit the galactic center, gas clouds swirl and collide, and the spiral arms sweep through the disk. Supernovae explode, sending shock waves through the interstellar medium, compressing gas and triggering new generations of star formation. Entire star clusters drift apart over millions of years, their members becoming indistinguishable from the background of the galactic field. The galaxy is both continuous and ever-changing, a system in motion, not just around its center, but within itself at every scale. The Milky Way's motion does not end at its own edges. It, too, moves through space, part of a larger collection of galaxies known as the Local Group. This group includes the Andromeda galaxy, the Triangulum galaxy, and about 60 smaller satellite galaxies, many of them dwarf systems orbiting the larger ones. The Milky Way and Andromeda dominate the group, and their mutual gravity binds them together. Both are moving through space at hundreds of kilometers per second relative to the cosmic background, and they are moving toward each other at about 110 kilometers per second. In roughly 4 billion years, the two will meet. When galaxies collide, they do not crash in the way solid objects do. The space between stars is so vast that even during a merger, few stars actually collide. Instead, their gravitational fields interact, distorting and reshaping each other's structures. Tidal forces stretch the galaxies into long, luminous streams of stars. Gas clouds compress, igniting waves of new star formation. Over the course of billions of years, the two galaxies will merge into one larger system, likely an elliptical galaxy. For any life that might exist on planets then, the night sky would look dramatically different, filled with vast arcs of light, new clusters, and a slow, majestic blending of two great star cities. Long before that merger, the Milky Way's motion continues unimpeded. It drifts toward the Andromeda galaxy, and also toward a much larger structure beyond, the Virgo cluster. This is a vast collection of thousands of galaxies about 50 million light-years away. Both our galaxy and Andromeda, along with other members of the local group, are falling toward the Virgo cluster, which itself is part of an even greater structure called the Virgo supercluster. These layers of motion extend outward almost without limit, each one part of an even larger flow. At the largest scales, the Milky Way and all nearby galaxies are moving through the universe as part of a vast cosmic web, an intricate network of filaments and voids, formed by gravity, acting over billions of years. Galaxies are not scattered randomly. They gather along threads of dark matter and gas that stretch across hundreds of millions of light-years. The Milky Way's motion follows the gravitational pull of this web, drawn toward regions of higher density and away from the great voids that make up most of the universe. Measurements of the cosmic microwave background, the faint radiation left over from the Big Bang, show that the entire local group is moving at about 600 kilometers per second relative to this ancient light. That means the Milky Way, Andromeda, and their satellites are all drifting together through space toward a region called the Great Attractor, a concentration of galaxies and dark matter that lies hundreds of millions of light-years away. Beyond even that lies another gravitational center, the Shapley supercluster, which continues to draw entire clusters toward it. On these scales, motion never stops. It simply merges into larger and larger flows. The Milky Way's endless motion is not chaotic. It is governed by the same laws of gravity and inertia that shape the motion of the planets and moons. But the scale changes the experience. The forces that hold the galaxy together operate over distances so vast that even light takes tens of thousands of years to cross them. The result is a kind of slow grace, a motion that is both constant and almost imperceptible. Stars orbit silently. Clouds of gas drift and collapse. The galaxy rotates once every few 100 million years, but it never stops turning. Within that rotation, the story of the solar system unfolds. The sun moves with its local stellar neighborhood, a small group of stars traveling in roughly the same direction. Some of these stars, such as Alpha Centauri and Sirius, are nearby companions in this slow migration. They share a common motion, part of a larger pattern known as the local standard of rest. Even among neighbors, each star has its own peculiar motion, a slight deviation from the average. Over millions of years, these differences cause the positions of stars to shift across the sky. The constellations we know today are temporary arrangements, changing subtly over time as the galaxy's rotation carries the stars along. This slow transformation connects cosmic motion to human perception. The sky that ancient civilizations saw was not the same one we see now, and the sky seen millions of years from now will be different still. Stars that are close to us move more noticeably, while distant ones seem fixed. This creates the illusion of permanence. Even though nothing in the galaxy remains where it is for long, everything drifts. Everything evolves, but so gradually that a single human lifetime captures only an instant of the movement. The Milky Way's motion also affects the environment around the Sun in subtle ways. As it travels through the galaxy, the solar system passes through regions with different densities of gas and dust. Sometimes it moves through relatively empty space. At other times, it encounters denser clouds. These passages can influence the heliosphere, the bubble of charged particles surrounding the Sun, slightly compressing or expanding it. They may also affect the cosmic rays that reach Earth's atmosphere. Though these effects are minor on short timescales, over millions of years, they become part of the long-term rhythm of the planet's environment. The galaxy's motion extends beyond the physical into the temporal. The stars we see now were not always there, and many of them will vanish from view as they age and die. New stars form in the spiral arms, replacing the old. The galaxy is constantly recycling itself, converting gas into stars, stars into supernovae, and supernovae back into gas. The elements forged in those explosions, carbon, oxygen, iron, are dispersed into space, where they become part of new generations of stars and planets. The very atoms in your body were once part of that cycle, born in ancient stars that lived and died long before the Sun existed. You too are part of the Milky Way's motion. Your matter is drawn from its endless circulation. If you could somehow perceive this motion in real time, it would look almost still. The distances are so vast, and the time scale so long, that movement becomes invisible to the eye. The stars would seem fixed, even though each one is moving at tens or hundreds of kilometers per second. The galaxy would seem frozen, even though it is constantly evolving. This is the paradox of cosmic motion. The greater the scale, the slower it feels, not because it actually slows, but because our perception cannot grasp the immensity of the distances involved. The Milky Way's endless motion is a quiet story, one that has been unfolding for 13 billion years. It began as a cloud of gas in the early universe, collapsing under gravity and spinning as it formed the first stars. Over time, smaller galaxies merged with it, adding their stars and shaping its spiral form. Even now, the Milky Way continues to grow, consuming small dwarf galaxies and absorbing their stars into its halo. These mergers are part of its natural evolution, small adjustments in an unending process of assembly. Every rotation of the galaxy brings change, but the overall pattern remains. The spiral arms persist, the core remains dense, and the stars continue to orbit in balance. From our tiny corner of this structure, we see only a fraction of what exists, but every part of it, from the central black hole to the farthest halo star, participates in the same grand motion. The Milky Way does not stand apart from the universe. It is one thread in a vast, interconnected fabric, moving in harmony with everything else. As it moves, so do we, carried within one of its arms, orbiting our sun, spinning on our world, drifting with the entire galaxy through the universe. The sense of stillness we feel is the quiet of perfect motion, a balance so complete that it feels like rest. Yet beneath that calm, everything continues, following the same unbroken rhythm that has no beginning and no end, moving forever onward through the cosmic sea. Each star, each planet, and every atom within us is currently drifting through a neighborhood of light where entire galaxies are the neighbors instead of worlds. The large Magellanic Cloud floats in the southern sky, a ghostly smudge of light, roughly 160,000 light-years from our home, while its smaller companion, the Small Magellanic Cloud, drifts at a distance of around 200,000 light-years. Both are irregular galaxies, lacking the symmetrical, graceful spiral structure that defines our own Milky Way. Their distorted shapes are not accidents of nature. They are the physical records of gravitational struggle. As they orbit us, they are being tugged and warped by the immense tidal forces of our galaxy and by their interactions with one another. They are not merely distant observers. They are participants in a slow celestial erosion. Trailing behind these two companions is a long, invisible river of gas, known as the Magellanic Stream. It stretches across hundreds of thousands of light years, a bridge of hydrogen pulled out from the smaller galaxies by the relentless gravity of the Milky Way. This gas, though thin and cold, represents a future that has not yet been written. One day, this stream may fall into the outer regions of our galaxy, providing the raw material for a new generation of stars to ignite. Even now, these two dwarf galaxies are spiraling inward, bound by an invisible tether that will eventually pull them into our embrace. They will merge with us, their stars and gas becoming part of our structure, just as many others have done before them. This is how galaxies grow, not in isolation, but through a slow process of consumption and integration, a cosmic recycling that turns small neighbors into parts of a greater whole. What seems static in the night sky is actually a snapshot of a continuous, slow-motion transformation. The shapes we see, the spirals, the ellipticals, the irregular clouds are the histories of these systems written in light. The Milky Way's own elegant form was likely sculpted by these ancient encounters. About 9 billion years ago, our galaxy collided with a system known as Gaia Enceladus. The remnants of that ancient cataclysm still linger in the galactic halo, visible to astronomers as stars moving on tilted, elongated orbits that do not match the steady rotation of the disk. We are a mosaic of past collisions, a collection of swallowed worlds and absorbed stars, all held together by the gravity that defines our neighborhood. But our neighborhood extends far beyond these close companions. The local group is itself part of a much larger architecture, the Virgo supercluster, an immense gathering of galaxies spanning about 110 million light-years. Within this vast region are thousands of galaxies organized into clusters and long, thin filaments. Near its center lies the Virgo cluster, a dense heart containing over 1,000 galaxies bound together by their mutual attraction. The Milky Way and Andromeda lie on the outskirts of this supercluster, like quiet suburbs on the edge of a great city, being drawn slowly toward the denser, more crowded regions at the center. When viewed on even larger scales, the supercluster connects to other vast structures, forming part of what cosmologists call the cosmic web. This is the large-scale skeleton of the universe, a network of filaments composed of galaxies, gas, and dark matter, intersecting at dense nodes where clusters form. Between these filaments lie enormous voids, regions of such profound emptiness that almost nothing exists within them for millions of light years. Within this web, galaxies and clusters do not drift randomly. They flow along the filaments under the influence of gravity, moving toward regions of higher density. Our entire supercluster, including the Milky Way, is being drawn toward a mysterious region known as the Great Attractor, located about 150 million light-years away. Beyond that lies an even more massive concentration of galaxies, called the Shapley supercluster, which exerts a gravitational pull so strong it affects the motion of thousands of clusters across hundreds of millions of light-years. Our galaxy, along with everything near it, participates in this vast migration, moving through space not as an isolated traveler, but as part of an immense, interconnected pattern. This motion is how we measure the expansion of the universe itself. In the 1920s, Edwin Hubble discovered that distant galaxies are receding from us, and that their speed increases with their distance. This revealed that the universe is expanding not because galaxies are flying through space like debris from an explosion, but because space itself is stretching, carrying the galaxies apart like seeds on a growing fruit. The local group, bound by its own internal gravity, resists this expansion, remaining intact even as the larger universe grows around it. But beyond our immediate neighborhood, the expansion dominates. The farther a galaxy lies from us, the faster it appears to move away as the fabric of space between us grows. The space between galaxies is not truly empty. It contains the intergalactic medium, a thin, sparse gas of hydrogen and helium heated to millions of degrees. Though it is nearly invisible, it glows faintly in X-rays and radio waves, forming the material of the cosmic web's filaments. As galaxies move, they exchange material with this medium. Outflows from supernovae push gas outward, while gravity pulls new gas inward to fuel the birth of stars. The boundary between a galaxy and the space around it is dynamic, a constant exchange of matter and energy that never rests. Astronomers often describe the local group as a gravitational island in an expanding sea. The galaxies within it are bound together closely enough that they will remain linked even trillions of years into the future, long after more distant galaxies have moved beyond the horizon of visibility. Eventually, the Milky Way and Andromeda will merge, forming a new, massive elliptical galaxy, sometimes called Milkdromeda. The smaller dwarf galaxies will be absorbed as well, until our neighborhood becomes a single, lonely island of light. Over immense timescales, this merged galaxy will drift alone, surrounded by a growing darkness as the expansion of the universe carries everything else beyond reach. The stars within it will age, turn red, and eventually fade, leaving behind a colder, quieter cosmos. Right now, however, our galactic neighborhood is alive with motion and light. The Andromeda galaxy shines with 1 trillion stars, many younger and more luminous than our own. The Triangulum galaxy, smaller and more delicate, glows with bright regions of star formation. The dwarf galaxies shimmer faintly, some rich in gas and others nearly invisible, composed mostly of dark matter. Together, they form a dynamic community where each system contributes its mass and energy to the balance of the whole. Even within the Milky Way's immediate surroundings, we see the evidence of this ongoing exchange. Streams of stars, like faint rivers of light, arc through our halo, the remnants of smaller galaxies torn apart by our gravity. These stellar streams are the proof that the Milky Way is still growing, still consuming its neighbors in a slow process of accretion. Each star in those streams was once part of a smaller world, now stretched and absorbed into the larger whole. The study of our galactic neighborhood also offers clues about the universe's most mysterious component, dark matter. By mapping the motions of galaxies, astronomers can infer the presence of this unseen mass, which outweighs visible matter by about 5 to 1. The galaxies of the local group move as if they are embedded in a massive halo of dark matter that extends far beyond their visible edges, linking them together in a common gravitational field. Without this dark matter, the local group would not exist as a bound system. Its galaxies would have long since drifted apart. The very fact that the Milky Way and Andromeda are moving toward each other, rather than away, is evidence of the strength of this hidden mass. It is the invisible glue of the cosmos, the framework upon which all visible structures are built. Within this context, our place in the universe becomes both smaller and more connected. The Sun, the Earth, and all life here are part of a galaxy that belongs to a cluster, which belongs to a supercluster, which is part of the cosmic web that fills the universe. Every scale of structure, from the orbit of a moon to the motion of a supercluster, follows the same underlying principles of gravity and momentum. The stillness we perceive on Earth is a brief pause in an ocean of movement that extends far beyond anything we can see. If you could somehow drift outside the Milky Way and look back, you would see a glowing spiral hanging in the dark, with Andromeda shining nearby as another wheel of light. Between them, faint bridges of gas and scattered dwarf galaxies would fill the space, all moving in a slow, patient dance. The two great spirals would appear to move almost imperceptibly toward one another, their arms slowly aligning as gravity draws them in. Smaller galaxies would orbit like tiny companions following in their wake. The scale would be beyond human comprehension, but the motion would be smooth and certain a neighborhood bound by gravity and time. All of it, the Milky Way, Andromeda, the gas, the stars, is moving together through the universe, drawn toward distant concentrations of mass. It is a hierarchy of motion that stretches outward without a clear boundary. The galaxies that seem frozen in the night sky are part of an unbroken stream, flowing through space like leaves on a river too large to perceive from within. And somewhere inside that river, our sun drifts quietly, carrying with it the planets, the moons, and the small blue world where you sit. The stars around us are neighbors in every sense, close enough to see, distant enough to last beyond lifetimes, and all of them part of the same vast migration. Every night, when the sky is clear and the air is still, there is a faint blur above the horizon in the direction of the constellation Andromeda. It is easy to miss, a soft patch of light just barely visible to the naked eye. To most, it seems like nothing more than a trick of distant starlight or a thin cloud. But that faint blur is not a star. It is an entire galaxy, a vast system of 1,000,000,000,000 stars moving slowly through the dark toward us. Though it looks motionless, Andromeda is on a path that will one day bring it directly to the Milky Way. The two galaxies are separated by about 2.5 million light-years, an almost impossible distance to imagine, yet their mutual gravity has bound them together for eons. Every second, Andromeda approaches at a speed of about 110 kilometers per second. The motion is silent. There is no sound in the vacuum between galaxies, only the steady, mathematical pull of mass. They have been moving toward one another for billions of years, and for them, a collision is inevitable. This is not a collision of solid objects, but of gravitational fields, vast, diffuse structures made of stars and dust merging through the quiet physics of motion. If we could watch this process unfold in real time, it would appear frozen. The approach is so gradual that nothing would seem to change over a human lifetime. Yet, over millions of years, the pattern would become clear. The faint patch of Andromeda would grow brighter, its spiral shape slowly becoming visible to the naked eye. Over hundreds of millions of years, it would dominate the night sky, a glowing wheel of light stretching from horizon to horizon. Its stars would no longer be distant points, but visible structures, their combined light turning the sky into a luminous dome. Eventually, as the two galaxies came close enough, their halos would overlap, and the first stars from each system would begin to pass among one another. When we imagine two galaxies colliding, it is easy to picture destruction stars smashing together, systems shattered, chaos spreading across space. But the distances between stars are so vast that almost none will actually collide. Each star, even in the densest regions, is separated from its nearest neighbor by trillions of kilometers. When the Milky Way and Andromeda meet, their stars will mostly pass by without contact. What will collide are their vast clouds of gas and dust. These clouds, when compressed by the merging gravitational fields, will trigger immense waves of new star formation, lighting up the sky with the birth of 1,000 suns. The collision will not end the galaxies. It will transform them, filling the new system with generations of stars, born from the turbulence of their encounter. The process will unfold with a slow, heavy grace. Over the first few 100 million years of interaction, the galaxies will begin to distort. Tidal forces will stretch them into long, luminous streams, arcs of stars drawn out by the uneven pull of gravity. Each galaxy will send out tidal tails, great bridges of starlight that connect them as their central regions draw closer. After the first pass, they will separate again, drifting apart briefly before gravity pulls them back for another encounter. This will happen several times before they finally merge into one. The combined system that emerges will not be a spiral like the ones we see today, but a massive elliptical galaxy, a single, rounded glow filled with old stars and long streams of gas. By the time this happens, billions of years will have passed. The sun will be entering its final stages, growing brighter and expanding as it exhausts its fuel. The Earth, if it still exists, will no longer be a place for life, its oceans boiled away by a swelling sun. Yet, far above the scorched surface, the collision of galaxies will continue, unaffected by the fate of any single world. The universe moves on its own timescale, and its transformations unfold whether or not anyone remains to witness them. This future merger is part of a continuous motion that began long ago, a journey set in motion by the very dark matter that fills the space between us. The halos of dark matter surrounding each galaxy have likely already begun to overlap, exchanging momentum and energy, quietly shaping the orbits of 200 billion stars. Our place in the cosmos is not a fixed point, but a moment in a long unfolding transition where the very constellations we know are destined to vanish and be replaced by a sky we can only imagine. In the deep silence of space, the two great spirals continue their approach, drawn together by a force that has been pulling since the dawn of time. But as we look toward this distant union, we must ask ourselves what lies even further beyond, in the regions where gravity no longer holds sway, and the very fabric of the universe begins to pull apart. Current models suggest that the first encounter will happen in about 4 billion years, with the final merger completed roughly 6 billion years from now. These predictions are not mere guesses. They are based on incredibly precise measurements of Andromeda's velocity components, including a small, critical sideways motion that determines the exact angle of approach. It is a cosmic drift so subtle that it has taken decades of observation to confirm, yet it dictates the fate of 200 billion stars. Even small uncertainties in these calculations could alter the specific details of the encounter, whether we graze each other first or plunge directly into the core. But the ultimate outcome is certain. The two galaxies will merge. The vast, empty space between them, though it seems void to our eyes, plays a vital role in this coming union. It contains the intergalactic medium, a thin, hot gas that extends far beyond the visible boundaries of the spiral arms. As Andromeda and the Milky Way draw closer, their massive halos of gas will be the first to touch, long before the stars themselves ever meet. This interaction will generate colossal shock waves, heating the surrounding medium to millions of degrees and marking the first invisible sign of the coming union. Eventually, when the galaxies begin to pass through each other, this pressurized gas will ignite in spectacular bursts of star formation. The collision will act as a cosmic spark, lighting up the combined system with millions of new, brilliant blue stars. These stars, though short-lived, will outshine everything around them for a brief period of cosmic time, turning the merging galaxies into a lighthouse of creation visible from millions of light-years away. They will burn with an intense, fierce light, before eventually fading into the quiet dignity of white dwarfs. As this unfolds, the Sun and its planets, or whatever remains of our solar system billions of years from now, will continue to orbit the galactic center, drawn along by the shifting gravitational tides. The probability that our Sun will collide directly with another star is extraordinarily small, given the immense distances between them, but our position within the new galaxy will change forever. We may be flung outward into the distant reaches of the outer halo, or drawn closer toward the new, massive center, depending on the chaotic details of the gravitational interactions. From wherever we end up, the view of the night sky will be completely transformed. The familiar, thin spiral pattern of the Milky Way will be gone, replaced by a bright, diffuse glow filling much of the heavens, the luminous remnant of two giants becoming one. In the long term, After the merger settles, the era of star formation will gradually decline. The available gas will be consumed or heated to the point where it can no longer collapse into new suns, and the new galaxy will become a quieter, more stable place. The brilliant blue bursts of young stars will fade, leaving behind a population of older, redder stars that will define the galaxy's mature phase. The dynamic, swirling spiral of today will have given way to a serene, massive ellipse, a monument to billions of years of motion and transformation. This new galaxy, often called Milkomeda, will enter a phase of slow evolution, its structure stable, and its light dimming over trillions of years. The stars will continue to orbit the central mass for unimaginable eons, but with less activity and less change, a silent city of stars drifting through the dark. Even then, the motion won't stop. The merged galaxy will continue to move through space, drawn by the gravity of nearby clusters and the larger structures of the cosmic web. However, the universe around it will be changing. Dark energy, the mysterious force that drives the acceleration of the universe's expansion, will continue to push other galaxy clusters farther and farther away. Over unimaginable timescales, galaxies beyond our local group will drift so far that their light will be redshifted until it can no longer be seen. The local group, now merged into a single massive galaxy, will remain as one of the last islands of matter in an ever-growing sea of darkness. In this way, the journey toward Andromeda is not just an event waiting to happen in the future. It is a continuation of the same cosmic motion that has been unfolding since the universe began. Every orbit of every star, every drift of every galaxy, is part of this larger story, one of attraction, collision, and renewal. The Milky Way's slow approach toward its neighbor is simply one more expression of the universal tendency for matter to come together, to combine and reshape itself over the eons. If you could speed up time and watch this process play out from a distance, it would look like a slow, silent ballet. Two great spirals drifting toward each other, their arms reaching out, touching, merging, and finally settling into one. Light would ripple through them as new stars form, fade, and give way to a deep, permanent calm. The result would be a single luminous galaxy moving onward through space, its past written in faint streams of stars that trace the paths of the original systems. That journey is already underway. The gravitational pull that binds the Milky Way and Andromeda is acting now, imperceptibly, but constantly, every moment. The distance between us decreases by about 110 kilometers. Over the span of human history, that change is meaningless, a tiny fraction of the total distance. But over cosmic time, it adds up. Millions of years from now, the difference will be visible. Billions of years from now, the two will be one. If you could somehow step outside the galaxy, away from the glow of stars and the swirl of its spiral arms, and look back at it from the quiet between clusters, you would see something that most of the universe hides from view. You would see that the Milky Way, Andromeda, and every other galaxy you can imagine are not truly isolated. They are connected, stretched along invisible threads of gravity and dark matter that bind them together across unimaginable distances. The universe, though it appears empty, is woven with structure, a vast invisible web that shapes everything within it. This web is not made of light or ordinary matter. It is made mostly of something we cannot see, dark matter. Though invisible, it makes up the majority of the mass in the universe. The stars, planets, gas, and dust, everything that shines or can be touched account for less than 5% of what is actually there. The rest is hidden, detectable only through its gravitational influence. Without it, galaxies would fly apart. Without it, there would be no structure at all. No clusters, no stars, no galaxies, just scattered particles drifting forever through the dark. Dark matter reveals itself through motion. It is the silent hand that controls the way galaxies spin and the way clusters hold together. In the 1930s, an astronomer named Fritz Zwicky noticed something strange. Galaxies within clusters were moving far too fast to be held together by the gravity of their visible matter alone. They should have flown apart like sparks from a spinning wheel, yet they stayed bound together. Later, in the 1970s, Vera Rubin confirmed this on a smaller scale, showing that the stars in the outer regions of galaxies rotated at nearly the same speed as those near the center. According to the laws of Newtonian physics, this shouldn't happen. The stars on the edges should move slower, just as the outer planets in our solar system move slower than the inner ones. The visible mass simply wasn't enough to account for the gravitational pull required to keep those stars in place. Something else, something invisible and massive, had to be providing the missing mass. Since then, every observation has deepened the mystery. Dark matter doesn't emit light, it doesn't absorb it, and it doesn't reflect it. It doesn't interact with electromagnetic radiation in any way we can detect. It passes through ordinary matter almost as if it weren't there, yet it exerts a relentless gravitational pull, shaping the universe on every scale. Computer simulations of cosmic evolution show that dark matter formed the very first structures in the early universe, gathering into long filaments and dense nodes under its own gravity. Ordinary matter, the gas and dust that would become stars, fell into these gravitational wells, cooling and condensing to form the first galaxies. The luminous universe we see today is merely a thin layer of light draped over an invisible skeleton. This invisible skeleton, the cosmic web, is vast beyond imagining. It spans the entire observable universe, stretching for billions of light-years in every direction. Its filaments connect galaxies like the strands of a spider's web, intersecting at dense clusters where gravity is strongest. Between these filaments lie enormous voids, regions so empty that entire galaxies could fit inside them with room to spare. The contrast between these dense and empty regions is what gives the universe its large-scale structure, a pattern that has persisted since the earliest moments after the Big Bang. To visualize this web, astronomers use powerful simulations, feeding the laws of physics into supercomputers and letting them evolve over cosmic time. Starting from a nearly uniform distribution of matter just after the beginning, tiny fluctuations in density grow under gravity, forming a network of filaments. Over billions of years, these filaments merge and thicken, pulling ordinary matter into their centers, where galaxies form. When these simulations are compared with real observations, maps of galaxy positions across the sky, the resemblance is striking. The pattern of reality matches the pattern of the invisible. The structure of the cosmic web is hierarchical. On the smallest scales are stars and planets bound into systems. On the next scale are galaxies, vast collections of billions of stars. Then come galaxy groups and clusters, containing hundreds or thousands of galaxies. These clusters are connected by filaments, which themselves are part of larger superclusters, stretching across hundreds of millions of light-years. Every level is connected to the next, from the smallest orbit to the largest flow of galaxies. It is a continuum of motion where gravity organizes matter into a repeating pattern of knots and threads. The regions between the filaments, the cosmic voids, are almost completely empty, containing only a few atoms per cubic meter. These voids expand faster than the rest of the universe because they are less dense, pushing matter toward the denser regions. Over time, they grow larger while the filaments become denser and thinner, giving the universe a cellular appearance, a kind of three-dimensional foam where clusters of galaxies form the walls and the voids form the empty spaces in between. Even though dark matter dominates the structure, it remains ghostly. To study it, scientists rely on its ability to bend the path of light itself. According to Einstein's theory of general relativity, massive objects curve the space-time around them. When light from a distant galaxy passes near a massive cluster of dark matter, the cluster's gravity bends and distorts it, creating arcs, rings, and multiple images in a phenomenon called gravitational lensing. By measuring these distortions, astronomers can map the distribution of mass, both visible and invisible, in the lensing cluster. The result is a ghostly outline of dark matter, a map of something that cannot be seen directly but reveals itself through the geometry of light. These maps show that dark matter doesn't clump in the same way as normal matter. It forms smooth, extended halos around galaxies, providing the gravitational framework that holds them together. In some cases, dark matter appears to interact only through gravity, not even with itself, allowing it to pass through other halos without slowing down. One of the most famous examples of this is the Bullet Cluster, two colliding clusters of galaxies where the hot gas from the collisions slowed down and heated up, but the gravitational mass, traced through lensing, passed straight through. This suggested that the majority of the matter was invisible and non-interacting. Despite decades of research, the true nature of dark matter remains one of the greatest mysteries in all of science. It might be composed of new kinds of particles that interact only weakly with ordinary matter, or it might arise from modifications to gravity itself that we do not yet understand. Experiments deep underground, in space, and at particle accelerators all search for clues, waiting for the faintest sign of a dark matter particle interacting with a normal atom. But so far, the silence is absolute. The mystery endures, not because we lack data, but because the phenomenon is so elusive, shaping the universe completely while remaining hidden from direct observation. The cosmic web isn't static. It evolves as galaxies move along its filaments and merge at its intersections. The flows of matter within the web continue to feed the growth of clusters and galaxies even now, billions of years after the first stars formed. Streams of gas fall inward from the filaments, replenishing galaxies with new material for star formation, while energy from stars and black holes flows outward, heating the surrounding gas and influencing the next generation of structure. This exchange of matter and energy gives the web a kind of circulation slow, immense, and unending. The Milky Way itself lies along one of these filaments, part of a structure known as the local sheet, which connects our group to other nearby clusters. Within this vast network, we are moving toward a region known as the Great Attractor, a gravitational valley where more than 100,000 galaxies are being drawn together. It is our cosmic address, a map of motion and connection that shows how even our small corner of the universe is part of a network stretching across the cosmos. This invisible web changes everything we know about the void, proving that the spaces between galaxies are not empty, but filled with the silent, guiding presence of the unknown. Yet, as we trace these filaments to the farthest reaches of the observable universe, we find that the web itself is being stretched by a force even more mysterious than dark matter. This relentless expansion, this stretching of the very fabric of existence, occurs against a background that remains constant, faint, and all-encompassing, a soft glow of radiation that fills every direction of the sky, everywhere, all at once. It is not the light from burning stars, nor is it the reflection from ancient drifting dust. It is the afterglow of the universe itself, the remnant heat from the very moment it began. This background, known as the cosmic microwave background, is the oldest light we can ever hope to see. It is not merely a backdrop. It is the foundation upon which all motion takes place, the silent breeze that moves through the fabric of space and time, carrying the memory of the beginning into the present. To understand what this background truly is, we must imagine the universe as it was nearly 14 billion years ago. In that primordial era, the cosmos was small, unimaginably hot, and incredibly dense. It was filled with particles and light tangled together in a seething, roiling plasma. In that early state, light could not travel freely. Photons, the particles of light, were constantly scattered by free electrons, bouncing around in a fog so thick and chaotic that nothing could move in a straight line. The universe was bright, yes, but it was opaque, a glowing, impenetrable cloud of radiation and matter too dense for light to escape. Then, as the universe expanded, it began to cool. After about 380,000 years, the temperature dropped enough for electrons to finally combine with protons and form neutral atoms. This event, which astronomers call recombination, changed the nature of reality forever. With the free electrons now bound safely into atoms, light no longer scattered constantly. Photons could finally travel unimpeded through the vastness of space. The universe became transparent, and the first light, that ancient radiation, began its journey outward into the void. It has been traveling ever since, stretching and cooling with the expansion of the universe until it now fills the cosmos as a faint microwave signal, detectable in every direction. This light is the cosmic microwave background, or CMB for short. It is a snapshot of the universe as it was nearly 14 billion years ago, preserved in the radiation that surrounds us even now. To our eyes, it is invisible because its wavelength has stretched into the microwave region of the spectrum, far beyond the narrow sliver of light we can perceive. But with radio telescopes, we can detect it with startling clarity, a smooth, uniform glow that covers the entire sky with a temperature of about 2.73 Kelvin above absolute zero. It is the cold, persistent whisper of the universe's beginning, still present everywhere, passing through your room, through the trees outside, and through your own body at this very moment. The discovery of this ancient glow happened almost entirely by accident. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were testing a massive horn antenna at Bell Labs in New Jersey. They were troubled by a faint, persistent noise that they couldn't explain. It didn't matter where they pointed the antenna or what time of day it was. The signal was always there, a steady hiss that refused to fade. They cleaned their equipment, checked for every possible source of interference, and even went so far as to remove nesting pigeons that had taken up residence inside the antenna, scrubbing away what they politely called white dielectric material. Yet, despite their efforts, the noise remained. What they had found, unknowingly, was the echo of the Big Bang, the background radiation predicted by cosmologists as the residual heat from the early universe. Their discovery confirmed a key prediction of the expanding universe model, showing that the cosmos had indeed begun from a hot, dense state and had been cooling and stretching ever since. Since that accidental discovery, our measurements of the CMB have become increasingly precise. Satellites like COBE, WMAP, and Planck have mapped this radiation in exquisite detail, revealing not just its overall uniformity, but also its minute variations, differences in temperature as small as 1 part in 100,000. These tiny fluctuations are crucial because they represent the seeds of all future structure. These slightly denser regions in the early universe grew over billions of years under the steady pull of gravity, eventually becoming the galaxies, the clusters, and the long filaments of the cosmic web we see today. The CMB is, in a very real sense, the blueprint of the universe, an image of the moment when everything we know began to take shape. If you could see the cosmic microwave background with your own eyes, the night sky would look completely different. It would not be black with scattered points of starlight. Instead, it would be softly, evenly glowing in every direction, an even wash of light without shadows or boundaries. There would be no center to this glow, because the radiation comes from everywhere equally. Every point in space sees it the same way because it fills the entire universe. It is not something that exists outside of galaxies. It exists within and around them, permeating every atom, every planet, and every moment of space. And yet, the background is not perfectly uniform. Those tiny variations in temperature, a few microkelvin above or below the average, tell us the story of the universe's history. They show us where matter was slightly denser, where gravity began its long work of pulling gas together, and where the very first stars would eventually ignite. When scientists analyze the spectrum of this background light, they can measure the composition, age, and geometry of the cosmos with remarkable accuracy. It tells us that the universe is 13.8 billion years old, that it is spatially flat within a fraction of a percent, and that it is made mostly of dark matter and dark energy. But the CMB also reveals something else: motion. Although the background radiation is almost uniform, we can detect a slight difference in temperature between two opposite directions in the sky. One side appears slightly warmer, while the other appears slightly cooler. This dipole pattern is not a feature of the universe itself, but rather the result of our own motion through it. The Earth, the Sun, the Milky Way, and the entire local group are moving relative to the CMB at about 370 kilometers per second. Because of this motion, the radiation in the direction we are moving appears slightly blue-shifted, or warmer, while in the opposite direction it appears slightly red-shifted, or cooler. This effect, known as the CMB dipole, is the ultimate reference frame for motion. It defines what rest truly means in the universe. When we say the solar system moves through the galaxy, or the galaxy moves through the local group, we are describing motion relative to this background. The CMB is the fixed canvas on which all cosmic movement is painted. It is the closest thing the universe has to absolute stillness, even though it, too, stretches and cools with the passage of eons. You might think of it as a kind of cosmic breeze, not something that pushes or drifts, but a field of light that all things move through. The galaxies do not feel it as a wind, but their motion relative to it can be measured as if it were one. We are moving toward the constellation Leo through this ancient light at hundreds of kilometers every second. The entire Milky Way carries us in that direction, and the background light shifts ever so slightly as we go, forming a subtle gradient that wraps around the sky. This background not only tells us where we are moving, but also how the universe has evolved since its birth. The light we see in the CMB was emitted when the universe was only 380,000 years old, and since then, space has expanded by a factor of roughly 1,000. That means the wavelengths of the original radiation, which were once in the visible or infrared range, have been stretched into the long waves of microwaves. Every expansion of the universe stretches this light further, cooling it down. Long ago, the background glowed a bright orange-white, like the surface of a distant star. Today, it is invisible to human eyes, and its temperature has fallen to less than 3 degrees above absolute zero. Despite its faintness, this radiation carries immense information. It contains subtle imprints left by the matter and energy the light passed through on its way to us. As it traveled across the universe, it was deflected by gravity, scattered by gas, and shifted by the very expansion of space. By analyzing these tiny distortions through a process called gravitational lensing, scientists can map the distribution of dark matter and trace the growth of cosmic structure over time. In this way, the background light acts as a record of everything that has ever happened since its release, carrying within it the story of the universe's evolution. Every photon of the cosmic microwave background has been traveling for almost 14 billion years. Each one left the early universe long before there were stars, galaxies, or planets. Many of these photons have crossed the same regions of space where new galaxies would later form. Some have passed through clusters so massive that their paths were bent, their energy shifted slightly by the pull of gravity. By the time they reach our telescopes, they carry with them the fingerprints of all those ancient encounters. When a radio telescope captures them, It is detecting the oldest light in existence, light that has been moving unbroken since the dawn of time. In a very real sense, the cosmic microwave background is the temperature of the universe itself. Everything within space, every planet, every atom, every distant star is bathed in it. Even the darkest, loneliest regions of intergalactic space are not perfectly cold. They glow faintly at this background temperature. It is the baseline of all thermal energy in the cosmos. If you could remove every star, every galaxy, and every atom, this soft, ancient warmth would still be there, filling the void. Its discovery transformed cosmology from a field of speculation into a precise science. Before it was found, theories of the universe's origin were varied and uncertain, but the CMB provided direct evidence that the universe once existed in a hot, dense state and has been expanding ever since. It also provided a natural explanation for the large-scale uniformity we observe, the fact that distant regions of the sky look almost identical. Even though they are so far apart, they could never have communicated with each other at the speed of light. This uniformity led to the idea of cosmic inflation, a brief, exponential expansion in the universe's first fraction of a second that smoothed out irregularities and stretched tiny quantum fluctuations into the seeds of galaxies. Those primordial fluctuations are preserved in the CMB as slight temperature differences. When mapped, they form a delicate pattern of spots and swirls across the sky, each one representing a region where the density of matter was slightly higher or lower than average. It is strange to think that the universe's motion and its very shape can be read from something so faint and so quiet. The CMB is not like the light from stars, which flickers and burns with local energy. It is steady and omnipresent, like the hum of an old machine still running in the background of existence. It doesn't change perceptibly from one day to the next, but it defines the reference for everything that does. All the movement we experience, the turning of the Earth, the orbit of the Moon, the drift of galaxies happens within its glow. When you look at the night sky, it is easy to feel as though the stars are close, hanging in a dome just beyond our reach. They appear as pinpoints scattered across the same flat surface, as if they were all at a single distance from us. The truth, however, is far deeper and far stranger. The light that reaches your eyes from even the nearest stars has been traveling for years. From the more distant ones, it has been traveling for centuries, millennia, or even millions of years. And from the farthest galaxies, the light began its journey before Earth itself existed. To see the universe is to look through time as much as through space, and that realization changes the meaning of distance completely. The scale of our voyage through the cosmos is so vast that normal numbers lose their meaning. We measure space not in kilometers, but in the time light takes to cross it, a light year. The distance light travels in 1 year is nearly 10 trillion kilometers. The nearest star beyond our Sun, Proxima Centauri, lies just over 4 light years away. That is about 40 trillion kilometers. To put that into perspective, a spacecraft traveling at the fastest speed ever achieved by humans would take more than 70,000 years to reach just that first neighbor, a journey that would span nearly 3,000 generations of travelers before the first alien sunrise ever touched their hull. Beyond that first neighbor, the numbers grow so quickly that they become abstractions too large for the human heart to truly hold. Even within the familiar boundaries of our own solar system, the scale of existence is difficult to grasp. We think of the Moon as our companion in the night, yet it orbits Earth at a distance of about 384,000 kilometers, a distance that light, the fastest messenger in the universe, covers in just over a second. The Sun, the anchor of our world, is about 8 light minutes away. This means that every ray of sunlight you feel on your skin left the surface of the Sun 8 minutes ago. You are always seeing the star as it was, never as it is in the present moment. As we move further out, the time light takes to reach us stretches into the hours. From Earth to Jupiter is about 40 minutes by light, and to reach the cold, distant realm of Pluto, light must travel for more than 5 hours. The entire solar system, out to the very edge of the region influenced by the sun's gravity, spans roughly 2 light-years. It would take 2 full years of traveling at the speed of light just to cross the invisible boundary that separates our system from the vast, empty space between the stars. And yet, even that enormous space is just a small, quiet pocket within the galaxy. The Milky Way itself is about 100,000 light-years across. It contains hundreds of billions of stars, each with its own system of planets, moons, and mysteries. If you could travel at the speed of light, it would take you 1,000 lifetimes, 100,000 years to go from one side of our galaxy to the other. But no ship we have ever built can travel even a fraction of that speed. The fastest human-made object, the Parker Solar Probe, moves at about 700,000 kilometers per hour. At that speed, which feels like a blur to us, crossing the galaxy would take roughly 200 million years. The scale of motion we exist within is beyond any personal sense of time or distance. The solar system orbits the center of the Milky Way once every 230 million years. This means that since the age of the dinosaurs, Earth has completed just one single galactic orbit. The entire history of human civilization, from the first stone tools to the words I am speaking to you now, fits into a tiny fraction of a single rotation, less than 1/10,000th of a galactic year. All of human history has unfolded during a mere blink in the motion of our world around its star, and its star around the galaxy. These timescales make every familiar measure of time seem fragile and local, like a small clock ticking inside a vast, silent cathedral. The distances between galaxies are even more staggering. The Andromeda galaxy, our nearest large neighbor, is 2.5 million light-years away. Its light takes 2.5 million years to reach us, meaning that when you look at that faint smudge in the sky, you are seeing it as it was when early humans first began using tools. The Virgo cluster, one of the nearest major clusters of galaxies, lies about 50 million light-years away. The light from those galaxies began its journey when the dinosaurs were still the masters of the Earth. Beyond that lies the Coma cluster, hundreds of millions of light-years away, and beyond that still are superclusters, immense gatherings of galaxies stretching across hundreds of millions of light-years. At the largest scales, the universe is arranged in filaments and voids, forming the cosmic web that extends across billions of light-years. The entire observable universe, the portion we can see, is about 93 billion light-years in diameter. That figure is not the size of everything that exists, but only the size of the part from which light has had time to reach us since the beginning. Beyond that horizon, there may be more galaxies, perhaps an infinite number, forever beyond our observation. The light from those regions hasn't had enough time to cross the expanding space between us. They exist in the same universe, but they are permanently out of reach, lost in the distance. Even the concept of motion changes when we think on these scales. In everyday life, motion is relative. You walk across a room, drive down a road, or orbit a star. But in cosmic terms, everything moves at once. The Earth spins on its axis at about 1,600 kilometers per hour at the equator. It orbits the Sun at over 100,000 kilometers per hour. The Sun, in turn, orbits the galactic center at 828,000 kilometers per hour. The Milky Way itself moves through the local group at over 2 million kilometers per hour, and the local group drifts toward the Virgo cluster at roughly the same speed. Relative to the ancient light of the cosmic microwave background, our total velocity is about 1.3 million kilometers per hour. Each of these motions adds to the next, yet none of them can be felt by our physical senses. We are passengers in a system of continuous movement, so smooth and stable that it feels like stillness. If you were to trace all of these motions together, the spin of the Earth, the orbit around the sun's path through the galaxy, and the galaxy's drift through the local group, the resulting trajectory would be a complex spiral, winding endlessly through space. Each orbit overlays another, each motion nested inside a larger. The path of a single atom in your body, when extended across time, becomes a thread in that cosmic spiral, tracing a route through the galaxy that will never repeat. You have never been in the same place twice. Every second carries you thousands of kilometers farther along a path that extends beyond the reach of human imagination. The sheer size of these scales challenges the very idea of what a place is. On Earth, place is defined by familiar distances, meters, kilometers, maybe thousands of kilometers across continents and oceans. In the solar system, those measures expand into millions and billions. In the galaxy, light years become the only meaningful unit. Beyond that, even light years become too small to use. When describing the largest structures, astronomers use megaparsecs, millions of parsecs, where 1 parsec equals about 3.26 light years. Superclusters and filaments can span hundreds of megaparsecs, distances so vast that light takes hundreds of millions of years just to cross them. From such a perspective, our world becomes almost invisible. The entire solar system is smaller than a single pixel in the map of the Milky Way. The Earth itself is less than a speck. And yet, everything that has ever lived, thought, or wondered exists within that tiny space. The human mind evolved under skies it could not measure, yet it has managed to map the universe beyond its own horizon. The ability to even grasp the scale of our voyage is one of the most remarkable consequences of consciousness, the universe reflecting upon its own immensity through us. When scientists measure distances across the cosmos, they often rely on light itself as the yardstick. Because light travels at a constant speed, its journey over time allows us to map the geometry of space. The redshift of a galaxy's light reveals how much the universe has expanded since that light was emitted. Each photon we receive carries the record of both distance and time, allowing us to reconstruct a three-dimensional picture of the universe from the signals that reach us. The farther away something is, the older its light. Looking deeper into space means looking farther back in time, toward the moment when the first galaxies were forming, and eventually to the faint glow of the cosmic background itself. Because the universe is expanding, distance is not static. Galaxies are not simply sitting in space, the space between them is stretching. This means that the farther a galaxy is, the faster it appears to be moving away. The light from distant galaxies is redshifted, its wavelength stretched by this expansion. The relationship between distance and redshift gives us a way to measure the rate of expansion, the Hubble constant, and from that, to estimate the age and size of the universe. To appreciate these distances, it can help to compress them into a scale we can understand. Imagine the entire history of the universe, scaled down to a single year. In this model, the Big Bang would happen at the first instant of January 1st. The Milky Way would form in late March. The Sun and Earth would appear in early September, and life would begin by the middle of that month. Complex organisms wouldn't appear until December. And all of human history, every civilization, every memory, every war, and every peace would unfold in the final seconds of December 31st. In that same model, the distance from Earth to the nearest star would be the space between 2 grains of sand, while the nearest galaxy would be kilometers away. Within that scale, the motions continue. Each orbit, each rotation, each drift is part of the same grand pattern. When the Earth circles the Sun, it covers nearly 1 billion kilometers each year. In that same time, the solar system moves tens of billions of kilometers along its galactic path. The galaxy itself drifts hundreds of billions of kilometers through space, and the entire local group moves even farther still. Every moment, the position of every atom changes in relation to the rest of the cosmos. Nothing in the universe ever stays still, not even for an instant. This constant motion can be difficult to feel. The ground beneath you feels solid, the air calm. You do not feel the Earth spin, or its orbit, or the galaxy's drift. You see the stars as if they were fixed in place, though they are all moving at speeds that would terrify us if we could perceive them. Stillness is an illusion created by balance. Every motion is matched by another motion. The speed of the Earth's rotation is balanced by the curvature of its orbit, and that balance produces the stability that allows life to exist. The stillness we experience is not the absence of motion, but the perfection of it. If you could somehow observe the Earth from far away, far enough that the entire solar system appeared as a small, glowing dot, you would see that dot moving along a curved path around the Sun, which itself follows a longer curve through the galaxy. Zoom out farther, and the galaxy becomes one of billions moving along the threads of the cosmic web. From that perspective, every orbit becomes part of a larger motion, and the idea of direction loses its meaning. There is no up or down, no center or edge, only a continuous flow of matter and energy through space. The mind struggles to hold on to such scales because they exceed the range of our senses. We are built to perceive the world in meters and seconds, not light years and eons. Yet, through instruments, mathematics, and the persistence of curiosity, we can extend our awareness far beyond those limits. The scale of our voyage isn't something we can feel, but it is something we can understand. That understanding transforms our perspective, turning the night sky from a ceiling into an open sea. Every motion we trace, from the smallest vibration of atoms to the expansion of the universe itself, is part of the same continuum. The boundaries we draw between solar systems, galaxies, clusters, and superclusters are only markers of convenience. The reality is unbroken. The same physical laws apply at every scale. The same gravitational forces shape motion everywhere. The journey of Earth through space is inseparable from the motion of the Milky Way through the cosmic web. To know one is to glimpse the other. This scale also reveals a paradox. The more we expand our view, the smaller we seem. Yet the ability to perceive that smallness is itself something immense. Within the atoms of our bodies are particles forged in the cores of stars, scattered across galaxies, and reassembled into life that can look back and understand its own origin. In that sense, scale is not a matter of size alone, but of connection. Every point in the universe is part of the same continuum. There is no edge where motion stops, no fixed frame of reference outside the whole. The Earth's path through space is not separate from the galaxies, nor is the galaxies separate from the cosmic webs. They are different expressions of the same unfolding. Every rotation, every orbit, every drift is part of a single ongoing voyage, one so vast that it encompasses everything, and so smooth that it feels like stillness itself. The stars we see at night are not markers of separation, but traces of this unity. Each one is a beacon shining from a different point along the same web, a reminder that motion is not a journey from one place to another, but the continuous unfolding of the universe itself. The heavens seem eternal only because our lives are short compared to the timescales of change. This disparity between perception and reality creates a profound paradox. We are surrounded by motion on every scale, planetary, stellar, galactic, and yet we experience almost none of it directly. Our senses evolved for survival in a narrow range of experience, attuned to movement we can respond to, but indifferent to motion too vast or too slow to matter in our daily lives. That gap between the world as we feel it and the world as it truly is lies at the heart of the human sense of stillness. It is not ignorance, but perspective, a reflection of how life has adapted to stability in the midst of a restless universe. If you were to leave the Earth and drift into orbit, the illusion would begin to break. From the silence of space, the planet's rotation becomes visible in a way that ground dwellers can never fully grasp. You would see continents moving beneath shifting clouds, sunrise sweeping across vast oceans, and the velvet curtain of night advancing over the glowing grids of cities. The curve of the horizon reveals the planet's true shape, and the stars no longer rise or set. They remain fixed as the Earth turns beneath you. The motion becomes clear only when viewed from beyond the system that defines your frame of reference. The same is true for the solar system itself. From a distance, you could watch the planets circle the sun, each following its own elliptical path in a slow gravitational waltz. From farther still, you could see the sun and all its planets together, moving through the Milky Way like a family of travelers. But from within any one of these systems, the motion feels like stillness, because everything around you moves in perfect concert. This principle extends outward indefinitely. Within the galaxy, the stars share a common rotation. Within clusters, galaxies drift together through the void. Even on the largest scales, the cosmic web itself expands uniformly. At every level, motion appears still to what moves within it. Stillness, then, is not the absence of motion, but the perfect synchronization of it. It is the state in which everything moves together, and therefore nothing seems to move at all. The human sense of stillness is reinforced by the environment we inhabit. Gravity binds us to the Earth's surface, anchoring our bodies and our senses to the same reference frame. The air moves with the planet, the oceans move with it. Even the atmosphere's rotation is synchronized to a degree with the planet's spin. This coupling isolates us from the larger motions around us, keeping us unaware of the speed at which we truly travel. We exist inside a cocoon of stability created by gravity and inertia. That cocoon shields us from the turbulence of cosmic motion, allowing us to build lives on what feels like solid ground. Yet, through understanding, we can step beyond that illusion. When we learn how fast we move through space, when we calculate the speeds and distances, when we look through telescopes and see the light from distant galaxies shifted by their journey, the stillness we feel becomes part of a larger perspective. It doesn't vanish, but it changes meaning. It becomes not ignorance, but harmony. The calmness of being carried along perfectly by forces vast enough to include us completely. On the most immediate level, the feeling of stillness is what allows us to rest. When we lie down, close our eyes, and let our thoughts quiet, we sink into the same steady motion that carries the Earth through space. The pulse of the body slows, the mind drifts. And though the planet continues to spin beneath the stars, it feels as though everything has stopped. In that moment, our internal rhythms align with the rhythms of the world around us, the turning of the Earth, the cycle of light and dark, and the gravitational balance that holds oceans and atmosphere in place. Sleep, in that sense, is not a break from motion, but an immersion in it. The stillness we feel at rest is the body's recognition of balance with the moving world. There is also a psychological dimension to this stillness. Human thought seeks stability. We build calendars, clocks, and maps to make sense of time and place. We crave repetition and order, even as everything around us changes. The daily cycle of sunrise and sunset, the phases of the moon, and the return of the seasons are the visible aspects of deep motions that we cannot feel, translated into forms we can live by. Stillness becomes the experience of patterns so reliable that they define the boundaries of our awareness. But our perception of stillness isn't absolute. It shifts with context. On a windy day, the trees move, but the mountains do not. From an airplane, the ground moves, but the sky seems still. From space, the Earth moves, but the stars appear fixed. The sense of what is still and what is moving depends entirely on where we stand. There is no fixed reference, no ultimate frame of rest. What feels stationary from one perspective is in constant motion from another. Even the cosmic microwave background, the closest thing to an absolute frame, is itself changing, cooling as the universe expands. Stillness is always relative, always part of a larger movement. Yet that relativity doesn't make stillness meaningless. If anything, it gives it depth. The fact that we can experience peace, balance, and calm in a universe of ceaseless motion shows that stillness is not a property of space, but of perception. It is the mind's ability to find equilibrium within motion, to feel at home inside change. The human sense of stillness is not a mistake. It is a form of adaptation, a way of living comfortably in a moving cosmos. In this way, stillness and motion are two sides of the same reality. The universe moves, but it moves smoothly. Its laws are consistent, its patterns continuous. We move within it, and because we move as part of it, we feel still. The stars wheel overhead, the planet spins beneath us, and the galaxy drifts through the cosmic web. All of it happens in perfect, unbroken silence. The absence of sensation is not the absence of movement, it is the presence of balance. When you stand outside under a clear sky, breathing in the night air, you are part of that balance. You are on a rotating planet orbiting a star, carried through a galaxy that is moving through the universe. You are in motion through time and space, yet you feel no motion at all. That stillness is real, not as an absence of change, but as the harmony of all change combined. It is the calm of being carried within a system that moves perfectly, without friction or sound, through a vast and endless cosmos. And somewhere in that quiet, in that balance between motion and perception, lies the very thing that makes awareness possible. The sense of stillness is not a flaw in our understanding. It is the state that allows thought to exist, reflection to happen, and wonder to arise. It is the still point from which we can look outward and grasp the motion of everything else. The Earth moves, the stars move, the galaxy moves, and yet we can pause within that movement and see it for what it is. That pause, that feeling of calm in the midst of motion, is as much a part of the universe as the motion itself. It is the human sense of stillness within the endless flow of the cosmos. Motion is everywhere, and it has been since the first moment the universe began. It is the quiet principle behind everything we see, from the way stars form to the way light travels and time unfolds. To exist is to be in motion. The stillness we feel is only the balance of these motions, an equilibrium so complete that it gives rise to calm. Yet beneath that calm, the universe flows continuously. If there is poetry in the cosmos, it lies not in words or rhythm, but in that flow in the ceaseless movement that connects everything. When we think of motion, we often imagine it as something that happens in space, like a planet orbiting a star or a comet crossing the solar system. But motion is not limited to the movement of things through space. Space itself moves. It stretches, expands, and changes with time. The galaxies are not racing through a fixed background. The background itself is growing. The distances between galaxies increase not because they are flying apart, but because the space between them is stretching. This expansion carries everything with it, like dots on the surface of an inflating balloon, each one moving away from every other as the surface grows. On that scale, motion isn't a journey from one place to another. It's a continuous transformation of the fabric that defines place itself. The laws that describe motion, inertia, acceleration, and gravity are simple, but their consequences are profound. They shape the structure of the cosmos from the smallest particles to the largest clusters. In Newton's time, motion was seen as something that required a force to start or change it. But Einstein's theory of relativity revealed something deeper. Motion is about the geometry of space-time itself. Mass and energy curve that geometry, and the motion we see follows those curves naturally. What we call gravity is not a force in the usual sense, but the shape of motion through curved space. The poetry lies in that geometry, in the way matter tells space how to curve, and space tells matter how to move. Every motion in the universe follows this mutual relationship. On a large scale, galaxies orbit the centers of clusters, and clusters drift within the gravitational wells of superclusters. Every orbit, every drift, every expansion is an expression of the same fundamental principle, the curvature of space-time guiding motion. The same equations that describe the fall of an apple describe the paths of galaxies across billions of light years. In that sense, the universe has an internal coherence, a consistency that gives rise to its beauty. The physics that governs an atom in a laboratory also governs the movement of stars in the galactic core. This uniformity allows motion to be predictable, but also endlessly varied. From those simple ingredients, infinite complexity emerges. Consider the motion of light itself. It moves not because something pushes it, but because motion is its very nature. Light is constant, traveling at the same speed for every observer regardless of their own motion. That constancy defines the structure of time. It means that when you move faster, time slows for you. When you are near a massive object, time slows for you. Motion and time are inseparable, woven into a single shimmering continuum. The way we move determines how we experience the passage of time, and the way time flows determines how we move. Every step, every orbit, every cosmic expansion happens within that single interwoven system. From this perspective, motion becomes something more than a change of position. It becomes the unfolding of existence itself. Each moment is a new configuration of the universe's motion, particles arranged differently, forces interacting anew, energy shifting from one form to another. Nothing ever stops completely, even in the coldest, darkest regions of space, where particles still vibrate with zero-point energy. Absolute stillness does not exist. The universe continues to move, even in its quietest states. This persistence of motion is the reason why time cannot reverse itself. The second law of thermodynamics, the principle that disorder tends to increase, gives motion its direction. The arrow of time points forward because energy spreads out, because motion disperses rather than concentrates. Every event leaves a trace, and every change creates an irreversible record. The flow of motion through time is the process by which the universe evolves, and its one-way direction defines the meaning of before and after. When you consider all these layers together, the motion of particles, the motion of planets, and the expansion of space itself, what emerges is not chaos, but a pattern of extraordinary balance. The equations that describe this balance are elegant because they capture something fundamental about how the universe organizes itself. Even turbulence follows deeper laws of order. What we perceive as disorder is often just complexity too great for the eye to resolve. This same motion gives rise to structure, galaxies forming from clouds of gas, stars forming within galaxies, and planets forming from disks of dust and ice. Even on Earth, motion is the architect of form. The rotation of the planet drives winds and currents, the movement of tectonic plates reshapes continents, and the flow of water carves valleys and deltas. Within living systems, motion takes on new meaning, becoming the basis of metabolism and the flow of energy that sustains life. The molecules in your cells vibrate and rearrange constantly. The blood in your veins moves in pulses driven by your heart. Even your thoughts depend on the flow of electrical impulses through neurons. Consciousness itself is a pattern of motion within matter. When you think, you are participating in the same physics that moves stars, only at a different scale. The human body is a small universe of motion, an organized system maintained by balance. Every beat of the heart, every breath, and every neural signal is a repetition of the same cosmic principle, equilibrium in motion. Life exists not in opposition to motion, but because of it. If the universe were truly still, no energy could flow, and without flow, there could be no processes, no change, and no life. Existence depends on movement, and the calm we experience is the calm of dynamic stability. The elegance of motion arises from balance, from the interplay between inertia and force, between freedom and constraint. It is the same principle that keeps planets in orbit forward motion balanced perfectly against gravitational pull. The universe expresses its symmetry through motion, and the human mind, attuned to symmetry, perceives that expression as beauty. This sense of beauty also comes from our ability to recognize patterns across scales. The motion of clouds in the sky and the motion of galaxies in deep space follow the same general dynamics, governed by the same principles of energy and momentum. Even in apparent stillness, motion continues quietly. A stone resting on the ground seems unmoving, yet its atoms vibrate with thermal energy. Over time, the stone weathers and returns to dust, and the solid surface of the earth itself flows slowly under immense pressure. Nothing in the physical universe is ever truly static. Time guarantees motion, and motion guarantees change. There is a kind of humility in realizing that motion never stops, meaning that every configuration of matter is temporary. The stars we see as constant are burning through their fuel, destined to fade or explode, and even the atoms that make up our bodies will eventually disperse. This continuity connects the smallest with the largest, linking the vibration of an electron to the rotation of a galaxy. When you trace those patterns outward, you find that everything is part of a single, ongoing flow. The orbits of planets and the oscillations of light are expressions of energy seeking equilibrium. Motion is the universal language of change, and everything speaks it. In human culture, motion has always fascinated because it symbolizes both life and impermanence. But beyond metaphor, motion is the literal structure of existence. Every heartbeat is a repetition of the same cosmic principle, equilibrium in motion. When we step back far enough to see all the layers of movement together, from the smallest trembling of particles to the rotation of galaxies and the expansion of space itself, what we find is a single continuous motion without pause or edge. This is the quiet continuum, the calm within all motion, the underlying state of everything that exists. It is not a metaphor or a poetic idea. It is the simple, physical reality of a universe that never, for a single heartbeat, stands still. From the earliest moments after the Big Bang, every particle has been in motion, every field has been fluctuating, every region of space has been changing in relation to every other. That movement did not begin in time. It created time. The expansion of space, the flow of radiation, the formation of matter, all of it are expressions of the same continuity, the same dynamic fabric of existence that has no gap, no still frame, no frozen instant. When we try to imagine the end of motion, what we are really imagining is the end of change. We picture a world where nothing evolves, where time has stopped, and where the silence is absolute. But such a world cannot exist in the physical sense. Even at absolute zero, the theoretical point where all classical thermal motion ceases, a subtle movement persists at the quantum level. Particles fluctuate in and out of existence. Virtual fields shift and oscillate in a restless, invisible dance. The vacuum itself is alive with this ghostly activity, a shimmering energy that never quite settles. The stillness of space is not an absence of motion, but its most balanced state motion, so symmetrical, so evenly distributed across the void that it feels like peace. The quiet continuum is not static. It flows through everything, shaping and reshaping the cosmos, sometimes gently like a drifting cloud, sometimes violently like a collapsing star, but always in accordance with the same eternal laws. Galaxies collide and merge in slow-motion ballets that last for eons. Stars are born in the heat of gravitational collapse, live for billions of years, and eventually die, scattering their elements back into the dark. Atoms combine to form molecules, then separate to become something new. Particles decay and reform in a cycle that has no waste. Each transformation is local, brief, and finite, but all are connected through the same uninterrupted process that has been unfolding for nearly 14 billion years. If there is an ultimate pattern to the universe, it is not a pattern of repetition, but of unending evolution, an ongoing continuity of change that encompasses all things. From our human vantage, continuity is what gives the universe its coherence. The sun rises each day because the earth keeps turning. The stars remain visible because their light continues to travel across the deep. The universe expands because its energy keeps flowing outward. But on a deeper level, continuity is not about repetition. It is about persistence. The motion that began at the dawn of time has not stopped once since that first expansion. Every process in nature, every orbit, every cycle, and every vibration is a small part of that same continuum, an expression of energy that is never lost, only transformed. The idea that energy is conserved, that it cannot be created or destroyed, only changed in form, is one of the simplest and most powerful truths in physics. It is also one of the most profound. It means that nothing ever truly disappears. The energy of stars becomes the light that travels through space, the heat that warms planets, the chemical potential that drives life, and eventually, the radiation that fades back into the cosmic background. The cycle continues, not in circles, but in a constant flow from one form to another. Matter and energy are interchangeable, and their transformations are the heartbeat of the universe. This continuity extends through scales of space and time beyond anything we can intuitively imagine. The atoms in your body were once part of stars that lived and died billions of years ago. The calcium in your bones was forged in the final, frantic seconds of a supernova. The iron in your blood was born in the white-hot core of a massive star that exploded long before the Earth was even a thought. The oxygen you breathe was created in the fusion reactions of ancient stellar nurseries. Those atoms have traveled across the galaxy, through interstellar clouds, through the long chain of generations of stars, before becoming part of a living organism on a small planet orbiting an ordinary star. When your body eventually returns to the Earth, those same atoms will continue their journey into the soil, into the air, into other forms of life. Continuity does not just exist in the cosmos, it passes through us. This seamless flow of matter and energy connects every scale of existence. The same gravitational pull that guides the rotation of a galaxy also guides the fall of a leaf in a quiet forest. The same electromagnetic force that binds atoms together creates the light of distant stars. The same quantum fluctuations that filled the early universe still ripple through the vacuum of space beneath your feet. There is no dividing line between the large and the small, between the cosmic and the human. The continuum is unbroken, and we are part of it, living patterns of motion sustained by the same physics that governs everything else. Even death, when viewed through this lens, is not an end but a transition. The forms that life takes are temporary, but the matter and energy that compose them continue. The universe is full of such transitions. Stars burn through their fuel, collapse, and scatter their elements, giving rise to new generations of stars and planets. Planets change, atmospheres evolve, and life adapts. At every scale, endings feed beginnings, and beginnings are just new configurations of the same unbroken process. The continuum ensures that nothing is lost. Everything is reabsorbed into the larger flow. The quiet of this continuity lies in its scale. From within, It seems like stillness because it is too vast and too smooth for our senses to detect. Just as the Earth's rotation is imperceptible because everything around us moves with it, the universe's continuity feels calm because it includes everything. There is no external frame of reference from which to see it change. The expansion of space, the passage of time, the transformation of energy all occur together, leaving no contrast to measure against. The silence of the cosmos is not emptiness, but total inclusion. Even the ultimate fate of the universe, whatever it may be, is part of this same continuum. If dark energy continues to drive accelerated expansion, galaxies will drift farther apart until their light can no longer reach one another. Star formation will slow, then stop. The stars that remain will burn out, leaving behind white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even those will decay, evaporating through processes like Hawking radiation. The universe will cool, fade, and approach a state of maximum entropy, a uniform, cold expanse filled with faint radiation and the remnants of matter. That vision, sometimes called the heat death of the universe, is not a destruction, but a settling the ultimate equilibrium of all motion. Even then, continuity persists. The radiation still travels, the fabric of space-time still exists, and the quantum fields that underlie reality still fluctuate. The quiet at the end of time is not an absence of motion, but its smoothest possible form, the final symmetry where everything moves together at the same pace. The continuum remains as calm and complete as it was in the beginning. This understanding does not make the universe less alive, it makes it more astonishing. To realize that everything, including thought and feeling, emerges from this continuous movement gives depth to every moment of experience. When you breathe, the air that enters your lungs has been circulating through the planet for billions of years, exchanging atoms with oceans, rocks, and other living beings. The photons that reach your eyes when you look at the night sky have been traveling through space since long before the Earth existed. The water in your cells has passed through comets and clouds, through countless generations of cycles. You are the latest arrangement in an unbroken chain of transformations that began with the birth of the universe. Every action, every thought, every heartbeat contributes to this continuity. The energy you use to move or think comes from the sun, which in turn draws its energy from nuclear fusion powered by the gravitational collapse of hydrogen clouds that formed billions of years ago. That energy, once spent, radiates outward, warming the air, feeding plants, and returning eventually to the Earth and to space. There is no boundary where your motion ends and the universe's begins. The quiet continuum flows through you, invisible but constant, defining every process of your existence. What we call awareness, the experience of being, is itself a momentary configuration within this flow. The brain's activity, the patterns of neurons firing and interacting, is another layer of motion shaped by the same physical principles. Consciousness does not exist outside of the continuum. It is part of it, emerging naturally from the organization of matter and energy. The fact that the universe can generate beings capable of reflecting on its motion is not an accident. It is the result of the same laws that make stars shine and galaxies turn. In that sense, awareness is the universe recognizing its own continuity, seeing itself in motion from within. If you were to imagine the universe not as a collection of objects, but as a single process, a wave, a current, a continuum, you would find that there are no true separations, only gradients. Galaxies fade into intergalactic gas, which fades into the cosmic background. Matter dissolves into energy, energy into radiation, radiation into expansion. Everything transforms smoothly, without abrupt edges. Even the concept of a beginning, the Big Bang, is not necessarily a singular start, but a boundary in time beyond which our current understanding cannot see. The continuum may have no beginning or end in the way we think of them, only transitions between states. The quiet of this process comes not from slowness, but from balance. Every motion is countered by another motion. Every force is met with resistance. Every wave is matched by its echo. The result is not chaos, but a deep equilibrium that spans all scales. When we sense peace in nature, the stillness of a calm sea, the silence of a clear night, the steadiness of the horizon, what we are feeling is alignment with that balance. The Earth's rotation, the orbit of the moon, the pull of gravity, and the expansion of space, all combine to create a world that feels stable. The tranquility we perceive is not separate from the universe's motion. It is that motion, harmonized and continuous. To live within this continuum is to be both transient and eternal. Every form changes, but the process continues. Every life ends, but the energy and matter persist. Every star fades, but its light travels on, adding to the cosmic background. Continuity means that nothing is ever truly isolated or lost. It is all part of the same unbroken field of motion. When one system dissolves, its components become part of another. The dust of old stars becomes the material of new planets. The remnants of living beings become part of future life. The continuum preserves everything, not as a static memory, but as an ongoing transformation. The awareness of this continuity brings a kind of serenity. To recognize that the universe does not stop, that its motion includes you, and that your existence participates in its flow, can transform the way you perceive both time and self. The moments that pass are not losses, but transitions. The future is not a destination apart from the present. It is the continuation of the same unfolding. The quiet continuum means that you have never been outside the flow of the universe, not for an instant. Every thought, every breath, every heartbeat has been part of the same motion that began with the first expansion of space. When you lie still tonight, breathing gently in the dark, you are moving with the earth as it turns beneath the stars. The air that passes through you connects you to the atmosphere, the planet, the galaxy, and beyond. You are not a passenger on this journey. You are a pattern within it, one that emerges for a time and then transforms. The calm you feel when you rest, when you let the mind settle into the silence of the room, is the same calm that exists at the heart of all motion. The equilibrium of forces so vast and so balanced that they give rise to stillness. The universe has no edge and no pause. Its expansion continues. Its structures evolve. The same motion that began in the first light continues now, unbroken, through every particle, every wave, and every living being. The quiet continuum carries everything forward, not in haste, not in chaos, but in perfect, tireless steadiness. It is the flow beneath all things, the silent foundation of existence itself. As you drift now toward the edge of sleep, remember that you are held in this great, silent drift. If this journey through the moving stars has brought you a sense of peace, I invite you to leave a like or subscribe to Science for Sleep so we can continue to explore these wonders together. But for now, let the words fade. Let the weight of the day dissolve into the steady rhythm of your breath. The earth is turning, the stars are gliding, and you are exactly where you belong, in the middle of a voyage that never ends. Sleep now, in the embrace of the quiet continuum, the motion that never began, that never ends, and that simply is, always and everywhere, the calm and unending movement of the universe.